Okay, I see that it's 4 p.m. my time, so we're gonna start. So good morning, good afternoon, and good evening, everyone. I am Gilles Bellet, one of the program organizing committee chairs, and welcome to IPPW 2021 session 5, dedicated to Venus exploration. Before we start, I wanted to go over some rules and some informations. So first, all the content that you're gonna see today is getting archived and will also be available on the International Planetary Probe Workshop YouTube channel within a week. If you go there, you will also be able to see the different material from session 1 to 4, which have already been uploaded. Secondly, the meeting itself is also being recorded and will be available on the previous mentioned platforms. Finally, please do not unmute yourself during the webinar. All questions must be addressed through the chat box. We will be moderating the mics and kick any person that insists too much on making themselves audible. And with that, have a great session, everybody. And now I will hand over to Jim, Robert, Patricia, Ashley, and Colin.
Good morning, everybody. Thank you, Gilles. I would like to welcome everybody to today's IPPW virtual session on Venus exploration. Our other session coordinators here are Robert Buchwald, Pat Beecham, Ashley Cozen, and Colin Wilson. My name is Jim Cutts. I'm a JPL, and Colin Wilson of Oxford University and I will be co-chairing today's session. This will include oral presentations and discussion sessions. The discussion sessions will include a discussion of the 5 poster papers, which you'll see in the agenda. They will not actually be presented here today. If you have not done so already, I hope you have, we encourage you to see if you can apply your multitasking skills to scanning them as we go through the rest of the program. I want to take this opportunity to thank the members of the poster committee at IPPW for putting together the poster program. You will note that there are no breaks in the program today, and we're going to rely on each of you to take appropriate opportunities to respond to calls of nature. One other point of information is that Gilles and Tim Bryce will be presenting the slides for the presenters. I think Tim is going to handle this from Pasadena. So that's essentially the arrangements that we're making for the talk today. Now to some specifics. These, of course, are exciting times for Venus. When we first had the idea of this session a few months ago, even when the papers were selected, we did not know that NASA and ESA, between them, would be selecting 3 new Venus missions. These selections have reinvigorated interest in Venus. In this session, we'll actually be looking at the future of in situ exploration, largely beyond the orbital Veritas and Envision missions and the Da Vinci probe, although the last oral paper will deal specifically with the contributions of Da Vinci. However, to begin our program today, we've invited Paul Byrne to review the future of Venus exploration. Paul is Associate Professor of Earth and Planetary Sciences at Washington University in St. Louis. He received his PhD in planetary geology from Trinity College, Dublin, and joined the Carnegie Institution as a messenger mission postdoc in 2011. In 2014, he moved to LPI in Houston as a postdoc. The following year, started as an assistant professor at North Carolina State University in Raleigh, North Carolina. And now he's moved most recently to Washington University in St. Louis. So welcome to Paul, and over to you.
Thank you very much, Jim. I just want to check, can you hear me okay? Great stuff. Okay, I am mid-move. I've started at WashU actually my first day was yesterday. So I'm in a hotel where I don't trust the Wi-Fi. So I'm going to turn my camera off and leave my mic on, but I wanted to say hi to everybody and that I am in fact a real person. And let's kick things off. So Tim, are you driving the slides? Or Gilles?
I think Tim is driving
Yes.
the side.
Yes, I'm driving it. It's Tim.
Okay, okay, great stuff. Thank you, Tim. Okay, so again, thank you very much, Jim and Colin and the entire organizing committee for IPPW to talk at this session. It's my privilege to share with you some of the kind of pressing questions that we still have to address, that what we're going to hear at IPPW in the session today will be primed to actually tackle and tell us the answers to. So I'm going to try and do 4 things in this talk. First, I want to introduce Venus. Perhaps not everybody here knows everything about Venus, so my goal is to give you kind of an overview of the vital statistics of the world. And then to talk about some of the key important science questions. There's a myriad questions that we don't know about Venus, that we haven't answered yet. My goal with these is I've picked 5 that are chiefly not going to be addressed by the recently selected missions, the Veritas, Envision, and Da Vinci missions that Jim mentioned. I'm going to talk briefly about those missions as a primer for some stuff you'll hear later in the session. And then I'm going to give actually the least amount of time, but I think in some respects the most important part, are some of the technology needs that we still have to address to actually fundamentally get at some of the core questions of Venus. And then I'm hoping that will, like I say, act as a primer to some of the talks we'll hear later in the session. So if we can go to the next slide, Tim, please. So just to give you kind of a brief overview of Venus, it is an Earth-sized world in the habitable zone of a main sequence G-type star. It is 82% Earth mass, 95% Earth radius, so its overall density is a little lower, but functionally on paper, it is very, very similar to Earth. It is made of the same stuff in about the same proportions. It orbits comparable distance to the sun to Earth. It's at 0.72 AU, so it's a little closer to the sun than we are, not very much more so. It's the same age as Earth, from several tens of light years away, by all measures. Venus and Earth are indistinguishable, and yet, like we know, and I'll describe, they are anything but geologically, climatologically, which is one of the big questions we have. But it is important to note that when we talk about Earth size and Venus size, in terms of our modern technological capabilities of telescopes, we cannot distinguish a world that's Venus-sized from Earth-sized. So every time you hear in the news about an Earth-sized world being discovered around a star, you may as well say Venus-sized. And we certainly don't know if they're Earth-like or Venus-like. Venus, Jim talked about this is a very exciting time, and I couldn't agree more. To get 3 missions, when we were hoping maybe to get 1. But what is interesting is if you go back to the dawn of the space age, Venus was the poster child. Venus occupied the place that arguably Mars does today. The first successful interplanetary flyby of another planet was by Mariner 2 spacecraft when it flew past Venus in 1962. Several months, I'm trying to think in terms of how that worked into the overall plan to send humans to the moon and beyond, but certainly very early in the 1960s, that mission opened our eyes to what we would see elsewhere in the solar system. And one of the most interesting findings of the Mariner 2 mission, it wasn't equipped with cameras, but it was able to detect, or in fact not detect, an intrinsic magnetic field at Venus. That was a surprise. And also determined that the lower atmosphere is extremely high temperature using radio emissions. And that was a surprise too, because prior to that point, there was not an unreasonable view that Venus might actually only be a little warmer than Earth. If you consider its distance to the sun and the amount of incident solar radiation that it gets. But in fact, there's no prospect of any kind of life or organic materials at the surface because we discovered the surface of Venus is extraordinarily hot. If you go to the next slide. So the sky, 97% CO2. The atmosphere is super rotating. The atmosphere rotates much, much faster along the planet's rotational axis than the solid body itself. I'll come back to that later. Early measurements detected a high D to H ratio, determined hydrogen ratio, suggestive perhaps that Venus had once lost substantial amounts of water, although the nature of that water and how and when it was lost remain major unanswered questions. There's a global cloud layer. The reason it looks beautifully cream in our sky, in our dawn or dusk sky, is this global layer of H2SO4 clouds. But interestingly, despite the fact that the atmosphere will kill you because it's toxic and that the clouds will dissolve you because they're extremely acidic and the pH is extraordinarily low. At the same time, the only other place in the solar system where you have room temperature and pressure conditions are at about 55 kilometers in the Venus atmosphere. And we have direct measurements from there thanks to the Vega balloons, 2 French-built balloons flown on the Soviet Vega missions in '85 that operated for about 44 hours. They circumnavigated about half of the planet. Let's call it a hemi-circumnavigation. And they told us, in fact, that this is a place where you can do science, but they are the only 2 aerial platforms, if you like, to have operated at Venus, a place where the conditions are generally clement in comparison to the surface. Next slide, please. And it's a surface where things are really grim. The temperature is that of a self-cleaning oven. It's about 470 Celsius. It changes depending on your altitude. Often people describe the surface as hot enough to melt lead. Personally, I have no intuition for what lead melting temperature is, but I do know that self-cleaning oven temperature is pretty bad. And the pressure is equivalent, again, at sort of the mean radius of the planet to about 960 meters under the water, about a kilometer under the water on Earth. So the pressure won't necessarily, we can build to those pressures, but the temperatures are a real issue. I'll talk about those at the end of the talk. We do know, however, from those few successful landed missions that were all exclusively Soviet in terms of soft landed and then sustained surface operation missions. When I say sustained, I mean about an hour. But we do know that the rocks are broadly basaltic, and there's a lot of stuff nuance I'm skipping there, but they're rocks we recognize. Some of the chemistry is interesting, but in terms of the major element bonances, these things are basaltic. And we have photos on the surface from the Venera 9, 10, and 13 and 14 missions. And 13 and 14 returned color images. They showed us images of sedimentary-like rocks. I'll talk a bit about that in a moment as well. And of course, the first recordings of sound on another planet. NASA's made much press copy about the interesting stuff we're getting from the Perseverance rover, which is terrific, including sounds. But the first place we ever had sound on another world was from Venus, from the 13 and 14 Venera landers. Next slide. One of the interesting things that we learned from NASA's Magellan mission, which was the first mission to give us essentially near global radar coverage, that got to Venus in 1990, operated through 1994, is that there's fewer than 1,000 craters in the surface. And this was surprising because we don't see that on any other world in the inner solar system except for Earth, a world largely devoid of craters. None is below 3 kilometers in diameter. There's a dearth of craters below 25 kilometers in diameter. That's probably taken to probably reflect the shielding effects of the contemporary atmosphere. Small impactors that would otherwise make a crater 3 kilometers in diameter or below don't get through to hit the surface. However, the distribution of craters on the surface of Venus is indistinguishable from random, which is to say that we can't be certain that it is a random distribution or not. It is not random with respect to geology, which is a subtlety that is often missed. And I think, in fact, there's more to be done to understand the geological history of Venus as recorded in its cratering record. But certainly, we do not see areas devoid of craters utterly, and others in which large craters dominate, like we would see, for example, on the other rocky worlds in the solar system other than Earth. And of course, there are no giant impact basins. The largest impact crater is fewer than 300 kilometers across, Meade crater. That's in stark contrast to Caloris on Mercury, or Sad-Pol-Aitken, or Imbrium on the Moon, or Argyre, Hellas, even Borealis on Mars. Again, something has acted to reset the crater retention age of Venus in the last perhaps billion years. Current estimates for the average surface age of Venus is around 700 million years, but there are huge error bars and uncertainties in that. Certainly different to what we see elsewhere in the inner solar system. Next slide, please. There is also some really interesting, tantalizing circumstantial evidence for a world that is still alive. Its geological heart yet beats. I personally am convinced there is active tectonic and volcanic activity taking place on Venus. We have no direct evidence of this. We have the detection of transient hotspots thanks to the Venus Express, ESA's Venus Express mission, which operated from 2006 to 2014, late 14, I think. Transient hotspots that were, particularly in areas that we know there are stratigraphically young volcanic deposits that are consistent with large, locally hot, relatively speaking, lava flows that then cool to ambient temperature. High thermal emissivity, again, as seen by the Venus Express spacecraft, that may correspond to geologically relatively recent unweathered basaltic lavas. We know that the amount of SO2 in the atmosphere changes. Pioneer Venus told us that. It's difficult to envisage the H2SO4 cloud layer remaining stable over geological time. It makes sense if it's been somehow replenished by something. And of course, two of the most dominant outputs of a volcano, at least on Earth, are H2O and SO2, as well as CO2. So if for nothing else, the fact that it's a big planet, really not much less big than Earth, why wouldn't it have lots of volcanism going on? But we don't know for sure. But there are hints. The same for tectonics. I know we'll talk about that as well. Next slide, please. And the long and short of it is, and this is a talk into itself, so I'm going to skip the details of this, but the point is right now, our current understanding of Venus presents with us two theories or hypotheses for the history of Venus. One is that it started off in the magma ocean phase, presumably like all worlds do. We think Earth probably did, we know the moon did. But its proximity to the sun was such that it was never able to cool down enough to condense water. And if that's the case, then this proto-Venus basically was doomed from the start, that it was always going to be an absolute hellhole. And but it may otherwise have not have been, except for its proximity to the sun. Solar distance is what did it. And it just started off ruined, and it's been ruined ever since. The second hypothesis on the next slide holds that perhaps it was more interesting than that. If you hit the next slide, please. And this possibility, which I'll talk more about in a moment, speaks to the idea that perhaps for a while, and recent climate models have actually placed firmer bounds on these models, on this hypothesis, that perhaps Venus might actually have been clement. It may even have been, as we would call, habitable conditions, perhaps for as long as 3.5 billion years, perhaps until about 1 billion years ago that changed. This is just a model, but the hypothesis holds that its proximity to the sun was not enough to kill it early on, that perhaps because of a hemispheric scale cloud, Venus was able to cool itself enough to condense water, to develop a hydrosphere, to perhaps develop some kind of volatile cycling system, plate tectonics or perhaps something else, and was able to regulate its own temperature until some kind of climate catastrophe occurred, perhaps within the last billion years, perhaps itself tied to volcanic activity. These ideas can be tested. I'll speak a bit about that in a few minutes. But the point is that we have these two models for Venus and we don't know which one is correct. And the point is here, either of these models has profound implications for our understanding of what we interpret for not just Earth's history and Venus's history, but the history and the evolution of large rocky worlds generally, including those that we are discovering around other stars. So understanding Venus is critical, not just to understanding Venus for its own sake, but to understand really the history of our own world, whether or not it could have gone down a different path and it was luck and fortuitousness that it didn't, or that Earth was always going to be okay and Venus was always not going to be okay, and that we can therefore extrapolate that then to what we see around other stars. So Venus really is a critical world, and these are some of the reasons why we should be exploring Venus, and I am so happy that we have these missions coming down the line. And of course, like we've seen with other worlds, missions beget missions. I hope it won't end with just these three. So if we go to the next part of the talk now, the next slide, I'm going to talk about 5 unanswered questions. There are dozens. I just picked these 5 as illustrative. Please do not see these as exhaustive or these are the only ones or perhaps even the most important ones. And I've tried to, because I look at stones, I'm a planetary geologist, I've tried not to bias this too heavily in favor of solid body and interior processes. But overall, take these as a sort of sampling of the kinds of things that we really need to continue asking of Venus. What was the planet's early history, right? It was measurements by Mariner 5 and particularly by Pioneer Venus, that D to H ratio, the deuterium-hydrogen ratio, that alludes to a history of substantial loss of water into space. And like I say, we don't know what the nature of that water was. Was it steam from a steam-rich atmosphere because the world never managed to condense into a hydrosphere proper? Or was it in fact an Earth's ocean's worth of water? And there have been studies, including ones in the Venus Express era, in which folks have extrapolated back how much water Venus might have lost. But those extrapolations rely on what the current escape rate is of Venus, which we have a rough understanding of because of today's sun and its activity. But we think that the early sun, the young sun, might have had much greater output of EUV radiation, which could have potentially driven far more material away from the atmosphere. So we don't know what the escape rate was integrated through time, which means that it's possible that Venus might have lost substantial amounts of water, oceans, plural amount of water, but we don't know this. But of course, the issue is there is at least some part of the parameter space that it permits Venus once having had oceans like Earth does today, and that is one of the things we need to we haven't answered yet. On the next slide, the second of these questions, what's the surface made of? We don't know what the ground is made of. We have limited chemical data taken over the course of an hour, in some cases, a little under 2 hours in another, to tell us what the rocks are made of. But these are really elemental, that's the wrong word. These are really basic analyses. They are not the kind of sophisticated chemical analyses that we can do in situ now that we know we can do, for example, on Mars. We saw from the Venera 9 landing site, blocky terrain. From the Venera 13 and 14 landing sites, we saw much smoother, flatter terrain. In fact, at the Venera 14 site, we see features that look like sedimentary rocks. We see quite a degree of morphological variability, but of course, because of the nature of the images, which have been reprocessed by people, and they do give us a sense of what the panoramas look like at those sites, those images are at such a different, vastly different scale to the radar data we have from Magellan that right now we don't have an easy way of linking landing site scale images and morphology and geology to what we see in radar data. So understanding what the rocks are made of through in situ chemical analysis, and also understanding what processes have shaped them to tell us why the landscapes look the way they do. This is an artist's impression of what the landscape looks like, because the real images are crap, because they were taken by these extremely rugged but fairly mechanically simple devices back in the 70s and 80s. I, for one, would love some 4K data from the surface of Venus. But the point is we don't really know what the rock is made of. And that becomes particularly relevant when it comes to the planet's tesserae, which we'll talk about in a moment. Next slide, please. So the tesserae are these, they occupy, well, what are they? It's a type of unit, or terrain type. It's not a geological word. It was coined by Soviet scientists in the 80s when they saw it with the Venera 15 and 16 radar data. Tesserae occupy about 7% of the planet's surface, and they are, I guess the easiest way to describe them is they're highly deformed rocks. They're highly tectonically deformed. There is sort of a formal definition of tesserae, which is two intersecting sets of fractures at high angles to each other. It's a stupid definition because rocks don't behave that neatly. But the point is, you can recognize tesserae when you see it because it's radar bright, it's much rougher. There's a variety of, again, highly circumstantial or less than fully robust data that suggests perhaps these tesserae, or at least the large exposures of them, which occupy much of the two large highlands, the terrae on Venus, Aphrodite and Ishtar Terrae, perhaps are somehow analogous to continents on the basis of their compensation depth and also perhaps their radar emissivity values. They're sort of compounded by the fact that in 1972, the Venera 8 lander touched down near-ish one of these tesserae, not on it by any measure, but near it, that perhaps was sampling rocks that might have been weathered off this locally high-standing tessera, and potentially detected elevated abundances of radiogenic elements that would be consistent with these things being elevated in basically continental-like materials. Someone once told me that there are more papers written about the Venera 8 measurements than photons detected by its instrument. So the short answer is we don't know what this material is made of. But where we see it, it is often the stratigraphically oldest material, it seems. That is to say that everything else around the area sits on top of it, suggesting that, at least in places, the tesserae is the oldest preserved material that's left on the surface. There have been many papers written about tesserae suggesting that perhaps they may date to a different climate era, if there was in fact a different climate era. There are also interpretations that are consistent that don't require there having been a climate catastrophe on Venus. It's not clear what the tesserae are, but they are more tectonically deformed than anything we see pretty much throughout the solar system, and that makes them an interesting place to study. The problem is they are rough, and so no one has attempted to land there yet because we have no real idea what kinds of hazards await a lander if it were to try and set down there. Next slide, please. We have recent evidence, we have recent work published on the basis of Magellan data, which are decades old at this point, that there's ongoing tectonic deformation, that there are stratigraphically young lava plains that themselves are deformed by tectonic structures, suggesting that that deformation is geologically recent. Now, does geologically recent mean in the last 100 years or in the last 10 million years? We don't know. We have no independent handle or constraint on the recency of that deformation. But we do know that there are places that show evidence of, in this case, the lithosphere fragmented into chunks that are moving. And this is a false color image. Well, it's radar imagery that I just applied a cool color stretch to. But the kind of yellowy stuff are the tectonic structures. They are radar bright, so they appear yellow. And the radar dark or smooth material appears kind of pinky and purpley. And you can see that there's sort of the cellular pattern where there are relatively undeformed low-lying areas that are delineated by bands of tectonic structures. And we published a paper a couple of months ago in PNAS describing our interpretation that these low-lying areas are mechanically coherent blocks that are jostling and shifting around. And some of that jostling and shifting seems to be recent. That is a kind of a key area I would like to go and look for evidence of seismic activity, ongoing seismic activity, as these things are moving. But the point is we have evidence that the surface is, at least in places, doing something tectonically. But we don't know how much or why. Major question. Next slide, please. And we also want to understand, why does the Venus atmosphere superrotate? This is an incredible image that Kevin Gill processed from Akatsuki data. Akatsuki, the JAXA mission operating in Venus orbit since 2015, has returned some stunning images in the infrared and ultraviolet of Venus itself, but has also been able to peer into different stratigraphic levels of the atmosphere to understand what the dynamics are. But fundamentally, and so the fact that you can see clouds that look like this, are almost like cirrus clouds. It's just amazing, wow, to get more data like this. But the atmosphere rotates about 60 times faster along that rotational axis than the solid body itself. Understanding why the atmosphere superrotates, the effect that, say, torques of that atmosphere has applied to the body to change its rotational speed, and fundamentally, when did it become like it is today, and what effect has that had on the body? They're massively open questions we don't have a good understanding of. We think that the Titan atmosphere also superrotates, but we have an easier to access natural laboratory in Venus than in Titan to try and understand the nature of superrotating atmospheres generally. So these are 5 exemplar key unanswered questions. Some of these will be tackled, if not answered completely, by planned and future missions, which I'll spend a couple of minutes talking about now. So if we can go to the next slide, please. As you are sure, I'm sure all of you are aware, we have these 3 missions that were selected by NASA in the last couple of months, and we are going back to Venus with Veritas. Veritas is going to be, and I'm not even going to try and attempt to spell out what that acronym is. And Da Vinci is also an acronym. Envision, thankfully, is not. But Veritas is going to return radar imagery, topographic data, INSAR data. It's going to give us a new insight into what Venus looks like on the surface at scale we've never seen before. It's also going to provide spectral measurements of the surface. There are windows. Nominally, you cannot see the surface through the atmosphere, but there are windows in the near infrared where you can. And Veritas is going to make an effort to characterize surface composition, at least in terms of the iron abundance of different surface materials, which in turn can be anti-correlated with the amount of silica in that rock. And that in turn can tell us a lot about the geological processes that have led to the formation of those rocks, the placement mechanisms, and even their melt generation if they're igneous. So Veritas is going to show us a world in 3D at a scale that we've never seen. We're going to see a whole new Venus with Veritas. It's going to be unprecedented, and I cannot wait to see what Veritas tells us. It's stablemate Da Vinci on the next slide. Da Vinci also has an orbiter, but I'm not really going to mention it to here because, in my view, at least the star of the show for Da Vinci is the atmospheric probe. Jim mentioned this in his intro. As it hurtles through the atmosphere all the way down to the surface over the course of about an hour, it's going to take repeated measurements and characterize the physical structure of the atmosphere, but it's going to take noble gas measurements. They in particular are going to be critical to answering our question of how much water was Venus born with, how much has it lost, and how is that material lost from the interior, how is it degassed? And that's going to be critical to place important constraints on these climate models we have for the evolution of Venus. It's also, the probe is going to take direct infrared, near infrared images of the tesserae. It's going to fly over and land, well, collide with Alpha Reggio, one of these tesserae exposures, a large one in the southern hemisphere. And it's going to show us what the tesserae look like. We've never photographed the tesserae because we've never landed on them. We've never had a lander return images of them. And because we've only ever seen them with radar, it's not the same as seeing a photo of something. And so the data from Da Vinci is going to be astonishing. And again, I cannot wait to see what those data look like. We'll hear a little bit more about this later in the session. And then on the next slide, we have Envision, which is ESA's winner of the M5, the Medium Mission Class 5 competition. And Envision is this beautifully complementary mission to Veritas. It's also going to fly a radar in a different wavelength. And it's going to produce high resolution radar higher in places, I think, than Veritas. I'm not privy to all the details of the mission, so I'm not entirely sure how Da Vinci or how Veritas and Envision will complement each other fully, or how they'll be designed to do that. But we are going to get some extremely high resolution data for the surface of Venus from Envision. We're also going to get spectral data of the surface through those infrared windows, and we are going to have subsurface radar sounding, which has never been tried or attempted at Venus before. That is also going to help peel back figuratively the cover of many of those vast plains, lava plains deposits on the surface to tell us what the ground looks like underneath. So those 3 missions are going to revolutionize our understanding of Venus. They are going to open up a Venus the way data from Mars Reconnaissance Orbiter and Mars Express and MER and you name it has shown us a new Mars. We're going to see a new Venus in the next 10 years, the next 20 years, and I can't wait. There are other missions in the pipeline too, and this reflects a renewed international interest. On the next slide, we have the Venera D mission. Venera D mission concept is slowly moving forward. The D is a Russian word that I won't make an attempt to pronounce. That basically means long-lived. The idea is that this extremely capable mission would feature a long-lived lander, would also carry a smaller augmentation that would operate for quite a long time, the Lysae system on the surface, which I'll briefly mention in a moment as I come to the end of the talk. But the idea of the Venera D mission is that it would basically give us a much better, much more modern take on the surface of Venus by doing detailed, sophisticated in situ chemical analysis of the surface. In fact, many of the remaining key questions for Venus require that we get in situ into the atmosphere and onto the surface. Venera D is going to try and tackle that. And even the Indian Space Research Organization on the next slide has announced plans for a Venus orbiter, the Shukrayan-1. There is a preliminary payload that has been selected, as I understand it. There's been less information about this mission than, say, some of the others, so I won't speak to it very much, but we do know that this mission is in development and simply reflects the international interest in Venus that is surely only going to grow as these missions that the US and ESA has selected are flown and begin to return data. We're going to presumably see more space agencies get involved or rekindle their interest in Venus. And as I understand it, JAXA has also at least somehow mooted that it's planning on launching Akatsuki 2, a second mission to visit Venus after Akatsuki, which has been hugely successful. I don't speak about that here. I don't know that much about it. And if someone else does, that'd be great. But I hope we see it. I hope we do see not just a decade of Venus coming forward, but decades of Venus. Now, for the last couple of minutes of this talk, I just want to briefly list some of the technological needs. And I've made this intentionally the shortest part of the talk, if you go to the next slide, really because this sort of, I'm hoping, helps set the stage for some of the things we'll hear about in the rest of the session, but also to get you thinking about the kinds of technological developments that we need to enable this new generation of Venus science. Jim mentioned that we're going to have orbiters, all 3 orbiters with Envision, with Veritas and Da Vinci. And we're going to be able to learn how to do a bunch of really cool stuff from orbit. There are many questions that we still need to be in orbit for, but some of the key ones require that we get into the skies, and things like technologies for aero capture and aero braking require development. Aerial platform altitude control. How do you control the altitude of your aerial platform? How do you work out which way it's pointing? Which way do you navigate? I know Colin will speak to a bit about this, but in terms of like long-lived operations in the Venus clouds with an aerial platform, preferably a variable altitude one that will last for tens or even hundreds of days, how do you control and navigate it? In situ seismological exercises. How do you detect seismic activity from an aerial platform? How do you detect it on the surface? And geophysical investigations. One of our major questions for Venus is, why does it not have a magnetic field? And when I said earlier that Venus doesn't have a magnetic field, we actually don't know for sure that it does. We just know that if it is there, it's extremely weak. Searching for a magnetic field with an aerial platform would be much, much more effective than doing it from orbit, and would also allow us to search for evidence of remnant crustal magnetization, which might speak to an ancient dynamo preserved in the rocks. And subcloud imaging, which we're going to hear a bit about today as well. If you can get below the clouds and mitigate much of the scattering from the atmosphere, we have a much better chance of understanding what the surface looks like in a way that radar doesn't really give us. If we go to the second last slide, there are also key technological requirements for in situ on the surface operations. High temperature memory and communication has been really remarkable work done so far in the last 5 or 6 years to understand how to develop high temperature electronics. And really remarkable work by folks done, for example, at Glenn, but we're still short things like memory and communication, which really impacts the ConOps, the concepts of operation for how we would operate on the surface of Venus. Fast instrument sampling, drilling, sample throughput and processing, so that if you are using a miniaturized QI TMS, for example, on the surface, and you aren't able to live for 60 or 100 or 300 days, and you really have to do everything in 5 or 6 or 7 hours. How do you make sure you move as quickly as possible to get those samples in, process them, and then broadcast those data home? Automated hazard avoidance and navigation. We saw how successful terrain relative navigation was for Perseverance to land in an otherwise completely inaccessible area of Mars in Jezero Crater. We need exactly that kind of technology if we're serious about landing on the Tesseract. Now, the direct images that Da Vinci atmospheric probe will give us will be hugely helpful. But if we have 3D high-resolution image data from, say, Veritas and Envision that we can program into the brain of a lander and then develop some kind of technology that allows that lander to actually, to some extent, guide itself onto the surface, that is going to open up the opportunity for us to land in situ on the Tesseract and tackle some of the most foundational questions we have for Venus. And finally, just ultimately, how do you work out how to live on the surface for longer than 8 hours? That's a critical question. I mentioned mobility here. Yeah, sure. Venus rover is a pipe dream. We're going to hear a little bit about a tesserated move. That's the right word, but wind-driven technologies for driving rovers on Tesseract. But if we were serious about doing a long-term nuclear-powered rover, even if it's 60 years away, let's start thinking now about what the kind of technology we need to get underway, the technology development we need underway to enable us to fly those missions in the coming decades. And then just on the very last slide that Tim went to just a second ago, I want to leave you with this sort of, kind of a multi-platform image idea of what this kind of smorgasbord of implementations that might be available to us. The future of Venus exploration is bright, but it's also multi-platform. Not a single type of platform can answer all the questions we have of this Earth-sized world. And it's going to require a mix of aerial platforms, both fixed and variable altitude, short and long-lived landers like Lysae, which is there in the center, and these long-lived landers that operate at ambient high temperatures. And then it's going to require orbiters, both as delivery vehicles, but also to relay back and take measurements from orbit themselves. Together, this is how we're going to understand Venus in the way that we must, to understand not just its own geological history, but that of our own world and large rocky worlds in general. Thank you very much.
Paul, that was tremendous. We are very tight for time this morning. We do have 2 questions that I want to present here, at least 2. First is from Samdata, does Titan also lack that many craters as Venus? Or does Venus's small number of craters say that the surface is active?
So off the top, I don't know if Ralph Lorenz is here. He might be able to answer this question more quantitatively than I can. The short answer is, yes, certainly the surface of Titan also shows the shielding effect of its atmosphere. But I think on the basis of the kinds of processes and landforms we see, the dynamicism of the ice shell is probably more reflective of the methodological cycle of Titan than large-scale tectonic and volcanic resurfacing, which I think is what we're seeing on Venus. But broadly, yeah, there are similarities. There's a great deal of comparative work we could do between those 2 worlds, yes.
Okay, the second question here, this is from Atul Garija. If there is ongoing active volcanism at Venus, will either Veritas or Envision, their radars, be able to detect surface changes induced by lava flow?
Yes, in fact, both missions are going to attempt to do INSAR, which would look for changes in the vertical relief of the landscape, which is something that we use widely on Earth to understand things like magma chamber tumescence. But critically, both missions, and particularly Envision, as I understand it, will carry a radar of the same wavelength as Magellan, albeit at a higher resolution. We'll be able to look directly for surface features changes in the intervening 4 decades or so. And that's exactly one of the critical things. People even try to do that during Magellan, but the data were never high enough. I've done it myself, tried to look for evidence to say a lava flow being a different length between cycle 1 and cycle 3 data, but the data aren't quite sharp enough for us to reveal yet. To Athol's question, that is exactly the kind of thing we're going to try and get at with those data.
Okay, finally, from Colin Wilson, you talked about the difficulty of landing on the Tesseract. What quantitatively do we know about the Tesseract in terms of slopes, buffers, scale of features for the purpose of designing landers?
So, I mean, and I'll make this quick, and we can talk about this later too. We actually know not some small amount about the tesserae on the basis of the radar emissivity data and backscatter data we have. Topography from Magellan is crap, and folks like Robbie Herrick have worked really hard to generate stereo. The altimetry, the default topography from Magellan is altimeter, radar altimeter data. Robbie and folks have developed stereo models, but even then, the tie pointing isn't great. So the point is that we don't really have a good sense of what tesserae look like in 3D. However, we do know on the basis of radar data that there are places inside tesserae, depending on which one you're talking about, that are smooth. And there are places that are extremely rough. Misha Ivanov did a really interesting write-up in the Venera-D Joint Definition Study Team report that I think is in 2017 or 2018, in which he basically tries to draw kind of a first-order comparison of landform between tesserae and landscapes we're more familiar with on Earth. And he compares some of the tesserae to the Grand Canyon on the basis of roughness scale. There are assuredly places inside the tesserae that are smooth and safe to land. The problem is those areas are often much smaller than any meaningfully small landing ellipse that we can expect a modern lander to have. If we were to have the ability to do what Perseverance did and land in a very, very small target area that we could quite easily set down in the radar smooth areas inside tesserae and then rove, for example. But again, like I say, that technology is probably decades away. Therefore, it's critical that we start on the path to develop that technology now.
Okay, great. Thanks, Paul. Wonderful start to the session here. We're now going to move on to the next talk. And this is by Colin Wilson, who's a researcher at Oxford, particularly in planetary atmospheres. He's worked on a number of Mars and Venus missions, beginning with Beagle 2 and ExoMars, to Venus Express, and now Envision. He was deputy lead for the Eve Venus balloon proposals of a decade or so ago. And notably here for IPPW aficionados, he hosted the last in-person meeting, which was in 2019. So Colin, take it away.
Great, thank you for that introduction. And it was a great pleasure hosting IPPW and a great pleasure to be here talking again. So after that, that great introductory talk, which was unfortunately terribly biased towards the surface, as of course we hoped it would be from Paul, I'm going to give one terribly biased towards atmospheric science, but more specifically talking about just narrowing in on what we can, what we should be trying to measure and the needs of measurement from an aerial platform on Venus. And just to say, you know, this may be a single author presentation, but it draws on work from a whole bunch of previous Venus mission proposals, including balloons. Just for context, oh, next slide, please. So just for context, this figure is from a recent review of future Venus exploration plans. Yes, we've just had 3 Venus missions selected, but no, our measurement needs and scientific needs for future measurements are not satisfied by those alone. There's certainly a large crossover between some of the measurements and science needs I'm talking about now from an in situ aerial platform with descent probes. You know, there's some sort of some of the instrumentation carried will be similar. If you want to ask about that, we can discuss that later. But for now, I'm going to focus mainly on the balloon platforms. Next slide, please. So just to cut to the chase, this is, you know, these have, the science pie has been sliced up various ways, but this is sort of my most recent version of that. So one is the first goal is to focus on the habitability of the clouds of Venus. This basically means look at all aspects of the environment, you know, the pressure and temperature environment, which are surprisingly Earth-like in the cloud deck. The cloud properties, because that's the, you know, the physical surfaces or liquids in which any life forms would have to operate. How much light availability is there? You know, how much UV, how much water availability, and then both good things in the forms of nutrients and minerals, but also harmful factors like acidity and radiation would any life forms have to deal with. This is a very helpful thing to focus on also because any engineering systems we send there, any balloons and instruments and subsystems also have to navigate all these factors. I haven't specifically listed for, search for life as one of the things we're going to measure. That'll be mentioned later. But certainly searching for the fate of, well, searching for biomolecules, molecules of biological origin, whether they are of Venus life or also whether they are molecules, organic molecules, which have been carried to Venus on, interplanetary meteorites and things like this. All these investigations will very much help to understand the habitability and potential of Venus for life. So habitability is the first goal. Second goal is chemical species, and in particular transport. The clouds of Venus represent a sort of gateway between the lower atmosphere, where it's hot and dense, and the upper atmosphere, where it's much more like the Earth's stratosphere. And so that combination of transport as well as composition is a key goal. In addition to understanding the role of transport in chemistry, there's also the dynamics. So Paul mentioned the circulation of Venus. Just remember that all planetary winds, all planetary atmosphere circulation are driven by sunlight, pretty much, with perhaps some excuses for outer solar system bodies, which we won't go into today. But for terrestrial planets, the sun is the engine, and then the question is, where is that sunlight absorbed in the atmosphere of Venus to drive that circulation? To what extent is it driven from the surface, with then waves and turbulence transporting that momentum upwards, and to what extent is it actually in the clouds of Venus that this engine room for the circulation is located. So we might have stopped this slide at this point, thinking that most of the science goals are related to the atmosphere, but actually you can get a surprising amount of science about the surface from balloon platforms. So we will hear later today about seismometry using infrasound. There's also search for crustal magnetism, imaging of the surface, and so on. So just to summarize, next slide, please. Just to hammer home those points, so in those categories of chemistry and meteorology and surface science, this is then what we would need to measure to address those science goals. This particular slide is largely borrowed from the Venus flagship mission study from last year. I have added in here a row about surface night side imaging, because that is a technology, the viability of which has been looked at and will be described later in this session. So I think perhaps the thing to focus on here is just on the surface science side, the number of different technologies available, techniques available to us to constrain surface properties and geophysical activity is quite surprising. So next slide, please. I'm now going to go through describing in more detail what this environment is in which the balloon platforms will have to operate. So the main convective zone is between 50 and 60 kilometers altitude. So here the atmosphere is by and large convectively unstable, so you get rising columns of air and sinking columns of air. This is where most of the clouds of Venus are located. To first approximation, we can imagine that they are much like the Earth's troposphere, with big cumulus type clouds and rising columns of condensing air with thick cloud and descending columns of air with thin cloud. But that is at this point a hypothesis, and we don't have that much observational evidence to support that. And this is where a balloon could really contribute quite a lot. Above 60 kilometers, the atmosphere becomes convectively stable, a bit like what happens when you go above 10 kilometers above the tropopause on Earth. And you have much more photochemistry dominated processes. You have different kinds of turbulence. In general, your balloon will have a more quiet ride with less turbulence. And so that's good for some other types of measurements. But the great thing about the balloon platforms being described here today is they will explore these different regions. Yes, so let us move on to the next slide, please. So going through different factors, environmental factors, one at a time. The winds, we know that Venus has very fast rotating winds. So broadly, they go about 100 meters a second, east to west. But it's important to remember that there's a lot of variability here. Typically, any instantaneous measurement of wind can vary from the mean by about 20 meters a second if you're talking about high near the cloud tops. And it's important to bear that in mind. So that affects the amount of time it'll take to go around the planet. It also affects your north to south drift. Next slide, please. So to illustrate that point, here are some simulations from probably the leading Venus circulation model from Paris, simulating the injection of a balloon, the release of a balloon at -10 degrees latitude, and just tracking its progress through this weather model. We might expect from mean wind fields that this would slowly drift towards the South Pole at a sort of constant rate. But what the model is suggesting is that actually it runs into all kinds of weather systems, and its stately progress polewards isn't stately at all. It oscillates, it gets caught up in weather systems. And while this is very helpful for seeing evidence of different kinds of dynamic phenomena, it's also a bit tricky when you're trying to predict where your balloon's going to crop up to communicate with it. So that's just something to bear in mind. Next slide, please. In terms of the vertical winds, we have the great luxury of having actually had these measured by the Vega balloons in the mid-80s, as Paul was mentioning. So they've been measured. Typically, the vertical winds are around 1 meter a second or less, with winds peaking above 2 meters a second. So if we have the next slide, please. I'll just talk about the inclusion of a wind sensor. We have proposed to include a wind sensor in these balloon missions. That often raises eyebrows because you think the balloon itself is acting as a very good wind sensor. If it moves northwards, it means the wind must be northward. So in terms of the horizontal wind, that is actually quite a good assumption. The balloons will respond to changes in horizontal wind and start tracking that. With response times typically of order 10 seconds. That's obviously dependent on wind speed and so on, which is fine for most goals. If you're interested in turbulence and wave phenomena at shorter time periods, then a wind sensor is really needed to help disambiguate drift of the balloon from responses to short-term turbulence. And that's important when we get to seismometry, for example. For vertical movement, it's more complicated because if the balloon isn't moving up or down, it could either be at equilibrium in still air, or, for example, it could be in a rising air column at above equilibrium. That you could still end up with a stable equilibrium. So to resolve that ambiguity, you need a vertical wind sensor on board to resolve that. And so this is at the top left. This is a picture of the Vega balloon payload suite, and it include a sort of a helical spinning device to tell whether there was the relative vertical velocity of the air was positive or negative. And so this just shows on the right how you have the anemometer reading at the top showing that you had descending air in the frame of the balloon. That was initially while the balloon was rising. So the balloon was rising and you had negative airflow going past it. And then by combining all that information, you can reconstruct what the actual atmospheric wind is. So it's quite an important system. We wouldn't have a big spinning thing anymore. Probably the best technology to use now would be an ultrasonic wind sensor because it's got no moving parts. This is a time of flight wind sensor. This particular one is a three-dimensional one. And so that way we can not only look at the vertical wind to measure that, but also characterize turbulence in some of the other dimensions. Next slide, please. In terms of clouds, so the first thing to mention is they are fairly diffuse with very small particles for the most part. Part of that is inevitable. If the particle gets too big, if the particle gets the size of our raindrops, then it'll do what raindrops do and fall rapidly, so it won't hang around. And our understanding of cloud droplet sizes are really based on incomplete measurements from a few occasional probes. So once again, the absence of rain may be something based on our infrequent measurements. In fact, cloud modeling, microphysical modeling on Venus does show gradual buildup of particles with then occasional rainout, and I think only a long-lived mission in the clouds could hope to measure that. It does offer a new challenge for us to deal with. We need to make sure that systems in the clouds can deal with such events like rain and condensation and deposition. So how exactly to define those qualification conditions, it still needs a bit of work, but it's underway. Next slide, please. In terms of composition, this is where it gets really interesting. So just how poorly constrained the composition of the clouds of Venus was highlighted by the discovery of phosphine reported last autumn. And people said, well, hang on, if there's all this interesting chemistry going on in the clouds of Venus, wouldn't we have already detected it from the previous missions? And the answer is we actually have very few measurements and constraints on composition from the previous missions, because they largely fell very rapidly through the atmosphere with instruments which by now are decades old. And there are a few outstanding questions. So normally we think of the clouds as being composed of strong sulfuric acid, but there are several pieces of evidence for non-sulfuric acid species. So one of the simplest is that we know, if you look at these lower figures, we know that there are haze particles below the clouds, some perhaps even quite large abundances of haze particles below the clouds. This can't be sulfuric acid because it's too hot for liquid sulfuric acid. It would be in vapor form. The other thing is we know that there are lots of UV features when we observe Venus in the ultraviolet, and those are not sulfuric acid. They don't have the right spectral properties for sulfuric acid. So we know that there's a lot of non-sulfuric acid in the cloud tops. One of the most intriguing things then is this top figure here is from the Vega descent probes, or Venera descent probes, which carried X-ray radiometry devices, X-ray fluorescent radiometry devices. They collected samples of the cloud droplets as they descended through the clouds, and then analyzed them with X-ray fluorescence to see the elemental composition. They found sulfur atoms, which is of course encouraging if we think it's sulfuric acid. But in the lower clouds, they found evidence or signs of phosphorus, even more phosphorus than sulfur. There have been constant questions of whether this is some artifact of the measurement. I think the best answer is to go back and measure it again. So in terms of what these things could be, it could be things related to volcanic volatiles, anything from the surface, dust, ash, and some specific compounds listed here. There's a lot to discover and has a lot of impact on atmospheric chemistry and potential habitability. Next slide, please. Just a shout out for measuring light levels in the atmosphere of Venus. This comes back somewhat to the engine room of atmospheric circulation. The plot on the right shows incoming radiation and shows that a lot of it's reflected to space, but some of it makes it down to the surface. Within the atmosphere, you don't get much sunlight, but you do get vast amounts of thermally emitted radiation in this thick atmosphere. This is what the greenhouse effect is all about. But slight variations, slight differences between the upwelling and downwelling radiation govern a lot of what the atmospheric circulation does. So, for example, the cloud base is heated from below by thermal infrared radiation, and that drives a lot of the convection. So understanding how solar heating and thermal fluxes drive atmospheric circulation is key to understanding how that works. And also, just looking at UV and light availability is important for understanding habitability and also understanding how you're going to power your various craft. So we'd very much like to measure light levels both in the visible wavelengths and in the thermal. If this is too technical and you want something more visual to imagine what it'd be like, next slide, please. A colleague of mine has made simulations of what you would see as you descend through the atmosphere. A disclaimer, what you see will be more interesting than this, because this was created using a homogeneous cloud model with no variation in the clouds, no horizontal variation in the clouds, just a vertical profile. If you then add horizontal variability, it'll be more interesting, and that's something we'd like to measure. There's a full video simulation of this, which you can find on YouTube. The link is later. But just to highlight some of the stills from it is, as you descend from above the clouds, you can see the direction of the sun. You're above the cloud layer. You can see the clouds below. And then next slide, please.
Colin, we're running out of time here. Can you wrap up in a couple of minutes?
Yeah, that's right. This is almost my last slide. So then by the time you get up down to 63 kilometers altitude, and this is where this is the top of the range of what you'd be looking at in a balloon mission, you've already lost sight of the sun. So if you can advance 2 slides, please. There you go. So this gives you one of the challenges is attitude determination. How do you know where you are and where you're going? You can't use a magnetometer. You can't use a sun sensor because you can't see the sun, and you can't use surface navigation. So here's some possible solutions. Basically, you either use a directional telecoms antenna. You might be able to detect the direction of the sun using radio frequencies, but otherwise it's going to be clever techniques with IMUs, which you'll have to use. Next slide, please. So just in terms of the flight plan, this figure is also available in the flagship report. We've got a whole range of things we can do once we use a balloon which can control altitude, but you might want to dwell in the upper cloud to look at to have a calm flight, to look at infrasound, or to look at the UV absorber in the upper cloud. You might want to be in the convective cloud where you have more habitable temperatures, and a balloon with vertical mobility lets us explore all these different areas. Next slide, please. So this is just a conclusion slide, just to reiterate that aerobots let us address all kinds of important science goals. And there have been loads of studies, and some form of balloons are viable now, with lots of development has gone into it. And we look forward to the input of this community to keep improving these technologies and the possibilities. Thank you.
Well, thanks, Colin. I think that was a great talk. I think to keep on schedule here, we'll move on into the next section here, into the next part 2, which you're chairing. We're going to have much more discussion of balloons and experiments from balloons. So I think there'll be an opportunity at the end of that session to really get into that in more detail. I don't see any question right now that's really compelling that we need to answer. Paul has been answering questions about his talk. Oh yes, here we go. Colin, what would be the deployment strategy for such a balloon? Would it be inflated on the ground or during entry or descent? And that was from Thomas Warin.
So hello, Thomas. Inflating on the ground would be a very challenging strategy because, of course, it's very, very high temperatures there. And so suddenly you would need to qualify everything for those temperatures. So instead, we would do what was done with the Vega balloons, which is deploy during entry, which in fact is not what's shown on your screen, but that's what was shown, demonstrated by the Vega balloons. Shall I carry on then with the second section?
Yeah, now I guess, yes, just going on into the second section, and just a reminder there that we will have some discussion of the poster talks in that session. So for those who have not looked at them already, see if you can find a moment or two to scan them while the oral talks are going on. And you can find them on the IPPW website for this session. So Colin, over to you.
Great. So in the second hour of our session, then, we're going to turn to the technologies needed for the balloon missions. So in particular, about a couple different balloon systems which allow some control over altitude. So without further ado, let's go to our first presentation. This is from Jacob Israelovitz, who's a robotics technologist at JPL. At JPL, his tasks bridge the interface between fluid dynamics and robotics, including the design of planetary balloons, rotorcraft, and underwater vehicles. So over to you, Jacob.
All right, thanks, Colin, for that introduction. Can everyone hear me all right?
Yes.
Yes.
All right, excellent. So hello, everyone. I'm Jacob Israelovitz, and I'll be talking to you all today about the technology development happening at JPL, making variable altitude aerobots for Venus. So I'll go over some of the developments we've been doing, our simulation work, and our test program for inflating and flying these balloons. So I'm talking on behalf of a very large team here at JPL and also at Near Space Corporation, who's our primary contractor for putting these balloons together. And I'm actually calling from Near Space today because we're doing balloon launches this week. So very exciting timing. Can we go on to the next slide? So a quick reminder about the Vega balloons. So the Vega balloons were they were secondary payloads on the Soviet Vega 1 and 2 landers. These balloons were extremely successful, although very small payloads. So just 7 kilograms gondola hanging below the balloons. They flew roughly 1/3 of the Venus circumference. And so what these really demonstrated is that a balloon platform can give you global scale mobility for your instruments, similar to an orbiter, but at the same time, you're taking in situ measurements with it, right? And that's the big advantage of balloons. So a lot of the development at JPL and at others has been looking at scaling that balloon technologies to larger payloads so that you can get a higher class of science return from a mission to Venus. I have an image here of the Valor 5-meter prototype balloon. This was a super pressure balloon that was scaled to a 44 kilogram payload. And you can see Jeff Hall in that image down there below. Next slide. So a lot of our technology development at JPL changed after the 2018 NASA Venus Aerial Platforms Study report. So this was a comparative study that looked at a bunch of different ways of exploring the atmosphere of Venus and compared their payload fraction versus their technology maturity. And one of the big winners from this study was variable altitude balloons. The reason being that there is only a small technology development on top of a fixed altitude balloon, but you get a much higher science return for the same entry mass. So what's also buoyed the support is in the last couple of years, there's been significant success in variable altitude balloons on Earth. So the most famous of which being the Google Loon project. They've been able to fly for I believe almost a year with a variable altitude balloon. And others have also been working on other concepts of variable altitude balloons on Earth. The next slide, please. So what we're looking for with a variable altitude balloon on Venus is duration of at least 100, or goal is 100 Earth days, long duration, we're talking about months. Over the course of that long duration, we expect to circumnavigate the Venus globe multiple times. Given the strong zonal winds on Venus, you expect to circumnavigate once about every 5 to 7 Earth days. The balloons we're looking at are passively stable in altitude, which means that if you turn off any actuation, then we stay at a single altitude. We're altitude stable, right? And so given wind and solar disturbances, we move a little bit, but we stay within the altitude bounds. If you turn on your altitude cycling, changing your buoyancy through moving around lifting gas, then you can change what the stable altitude is. So for our concepts at JPL, we've been looking at a single 10-kilometer band at Venus. This is 52 to 62 kilometers. And to achieve this altitude change, we need to change the volume of the balloon by roughly 4 times. So that's the big challenge, right? Our concepts are also very scalable in terms of the hanging mass. So we have point designs already from 100 kilograms to well over 200 kilograms. And this is, sort of targeting New Frontiers class payload size. And at least one of these point designs was incorporated into the Venus flagship mission study, with Colin Wilson talked about already earlier this session. Next slide, please. So this is how the balloon works. So we're actually a 2-balloon system. The outer balloon carries most of our buoyancy gas, and it is a 0 pressure balloon, meaning that the envelope is slack. The internal pressure in this balloon is roughly the same as the pressure outside. Inside the 0 pressure balloon, though, we have a second balloon, and this is our reservoir. So whenever we want to descend, we take excess gas from the outer balloon and we pump it into this rigid balloon inside, which acts like a tank. And so as we decrease our volume, our buoyancy goes down and therefore we descend. If we open up an orifice between the 2 balloons, then our balloon total volume expands again and we ascend, right? So there's a couple different ways of doing altitude control on Venus. This method, which is called pumped helium, is one method of doing so. It turns out it's the most power and efficient method for doing large altitude changes on Venus. We have an AAA paper that we can circulate to folks that are interested. There are, however, other architectures for doing this, and they all have other advantages. So Max de Jong is going to give a talk next talk, actually, on another way of doing this, targeting a lower altitude band. Next slide, please. So our technology development at JPL is on 3 fronts. First, we are building subscale prototypes, and this is an effort of selecting balloon materials based off of the expected Venus environments, and manufacturing balloons out of those materials and making them gas tight. So this is difficult because balloons that are designed for Venus are made out of a different type of balloon materials, and so making them gas tight is something that you need to be very careful with. So this is an image here on the left of some of the seam tape testing that we've been doing to make sure that our helium permeability is as expected. We're also doing controlled flight testing. So we have indoor and outdoor flights of flying these subscale prototypes. Our scale is roughly 1/3 at this moment. But if we're flying at roughly sea level on Earth, it's very similar to the densities that we expect to on Venus. And so the dynamics of the balloon are very similar, which is nice because we're also doing a large simulation effort to simulate the trajectories of these balloons. So we validate those simulations against our subscale experiments on Earth, and then we use them to predict what the full-scale performance is going to be for this balloon on Venus. Next slide. So this is a brief overview of the balloon materials we've been using. So the outer balloon, the zero pressure balloon, needs to be acid proof, right? It's sitting in the clouds of Venus, and so it's entirely covered in Teflon, right? The layer below the Teflon is a silver deposited layer, and this reflects most of the sunlight. So sunlight, while being very nice and abundant on the day side of Venus and good for solar power, it also heats our balloon. And the more it gets heated, the higher the pressure inside the balloon grows. And so we actually spend a fair amount of balloon mass in order to mitigate this solar heating, right? So Teflon is great for rejecting the acid, and the silver is great for rejecting the sunlight. But Teflon is not a particularly good balloon material because it's very stretchy. It doesn't take load very well. And this balloon needs to be deployed during EDL. So below the Teflon layer, we include a Kapton layer. So the Kapton is what gives our structural strength and is also our gas barrier for the helium. Our inner balloon, the superpressure reservoir, somewhat interestingly, it's actually allowed to leak a little bit of gas because if some gas is leaked out of the inner balloon, it just goes to the outer balloon and adds to power requirements, but not necessarily decreasing our mission life. So we can get away with a slightly less rigid requirement on the gas barrier on the inner balloon, which is interesting. So these are fabric balloons because we need to make them very strong and stiff. And so we've been making balloons out of both Spectra and Vectran. Spectra is our crutch to make balloons quickly. It doesn't, however, it can't survive the whole temperature cycle that we need for it to be on Venus. And so we've more recently been moving over to Vectran balloons. So our current prototype is a Vectran balloon with an inside urethane bladder. Next slide. So here's some of the prototypes we've been building up at Near Space Corporation. So on the left is one that's in the lab. It's a 4-meter prototype. This is a Spectra inner balloon. And on the left, you have our new balloon. This is a 5-meter prototype. This is using a full Vectran inner balloon and has an upgraded tape seam between the gores on the outside. Next slide. So this video might play. Yes, possibly. Okay, so this is a video of some of our flight testing happening in the lab. So we've been doing ascents and descents of the balloon and heavily instrumenting it with engineering sensors. So the goal here again is to match simulation data. So we've been putting a bunch of pressure transducers and thermocouples and such things, measuring everything we can and matching it to our simulation data. So we've been doing a fair amount of hangar testing this year, and we're planning outdoor flights this fall. Next slide. So in terms of our simulation side, we've been leveraging JPL's DARTS simulation package. So DARTS is used in a number of different NASA centers, largely for EDL studies. It's multi-model. It's a linked C++ solver, and what's great about it is you can swap different physics models on different modules and connect them all together, right? So our full model is very multi-model. We're it includes all the temperature nodes and atmospheric data and such. And so it's been a tremendous tool for being able to quickly simulate what we expect in the lab and on Venus. So these graphs are showing some of the comparisons we have right now between our simulation and the flights in the lab. And on the right, you can see our dynamic shape model for predicting the shape of the balloon as we pull gas out of the zero pressure balloon. Next slide. We've also been using the DARTS package in order to simulate our flights on Venus. So this top graph is showing a slow power descent from our top altitude of 62 down to a medium altitude of around 54 kilometers, and then a rapid ascent after that. So generally, our descents can be much faster than our ascents because our descents are power limited. It's whatever you can afford to put into the pump. Our ascents are very quick, and so it ends up being a somewhat instantaneous rising profile at a certain point on Venus. We can also use this model to predict the performance of specific point designs against certain Venus stressors. So at this point, we're baselining a stability margin of up to 3 meters per second of updrafts and downdrafts. This is based off the Vega flight data. And we can additionally mitigate some altitude disturbances by running the pump if need be, right? If we're okay expending power. Next slide. So in summary, we consider variable altitude balloons are key to the next phase of Venus exploration. We've begun our development of this technology at JPL after the 2018 NASA report. It's already been adopted as a primary asset in some of the decadal study mission studies. We consider this technology to be very scalable. We have a range of different closed point designs. And we're actively working on it. We've been selecting balloon materials, we've been testing them, we've been building balloons out of them, we've been floating them in the lab, and we plan to fly them on Earth. At this point, we're already validating our simulation tools against that indoor flight data, and we expect to fly outdoors later this year. So for more details on everything I talked about, we also have an AAA paper coming out this week. So feel free to reach out to me and we can send you an advanced copy. And with that, next slide. If you have any questions, feel free to put them in the chat, and we'll answer them if we have time.
Great, thank you very much, Jacob. Excellent talk. We have a first question in the chat is, how is the balloon deployed and inflated?
Sure, so actually that's something that we are very much working on. So the current plan for deploying said balloon is it's extracted. So the balloon is stored in a canister, and that canister needs to be airtight because you don't want the balloon, any leftover gas in the balloon, to start expanding it during cruise. This canister is opened when the back shell is pulled away from the heat shield by the drogue chute, right? So unfortunately, I don't have a graphic for this, so it'll have to be a future talk. So after we extract the balloon from the canister with the back shell, use a descent rate limiter to make sure that it comes out smoothly. And then you start inflating the balloons. So you have 2 different orifices, one for each balloon. And so you can select the timing accordingly. And you get the balloon fully inflated, actually a little bit below its final flight altitude. You drop the tanks, and then the balloon returns to its nominal flight altitude. So we get a little lower than, I think we drop down to 52 kilometers. We hover out at about 54. So.
Great, thanks for that.
At least that's the plan.
I suggest we move on in the interest of time. So this takes us to our next presentation, which is by Maxim de Jong. So Maxim is he is the CEO and chief engineer at Thin Red Line Aerospace, company specializing in soft goods development for manned and robotic space exploration. Maxim has a 40-year heritage applying these innovations in inclement environments around the world. Over to you, Maxim. We cannot hear you if you're speaking. Have we got Maxim connected?
Yes, he's connected.
Maxim, can you try speaking again? We can see your microphone icon, but we can't hear you.
Maxim, are you perhaps double muted?
I think he's
All right, we
disconnected
see
from
him
audio.
now. Maxim, you may
Shall
need
we?
to adjust your audio settings, make sure your mic is working.
Perhaps we can move on to the next talk, and then Maxim can rejoin us when available, when his technical problems are resolved. So in that line, then our next speaker is Rachana Agrawal. I'm afraid I didn't receive bio information for you, so I can say you're at Purdue University at the School of Aeronautics and Astronautics. So over to you.
Thank you. Good morning, everyone. My name is Rachana Agrawal. I'm a PhD candidate at Purdue University. I'm presenting on the architecture design for searching for life and science of life in clouds of Venus. Before moving forward, I'd like to thank everyone on the Venus Life Finder mission team and Breakthrough Initiatives for funding this study. Next slide, please. So this architecture design is part of the Venus Life Finder mission concept study, which we started last summer and which is led by Professor Sarah Seeger at MIT and co-led by Dr. Janusz Petkowski at MIT. Professor Sarah Seeger also has a talk next week about this study, so please listen to that as well. The goal of this study was to design a series of missions to search for life and science of life in the clouds of Venus. And the most interesting altitude range for the study was the middle and lower cloud layer, which are at temperatures suitable for life. Although there are extreme acidic and dry conditions in these layers, there are also unexplained chemical anomalies which motivate this astrobiology focused missions. And we believe that these are complementary to the 3 selected missions because they are not astrobiology focused. So science-wise, these are highly complementary. So we designed 3 different classes of missions, starting with a small probe mission, which is led by Rocket Labs and slated for 2023 launch. And Richard French also has a talk on it next week. Then the second was a balloon mission. I'm still on the last slide. Thank you. The second
Sorry,
was
Rachana, your volume dropped a little bit. Can you just speak a little bit closer to your microphone again?
Is this better?
That's perfect, thanks.
Yeah, so the second type of mission was a balloon mission, and we looked at a range of options with a constant altitude balloon and also a variable altitude balloon. And I'll be talking about the variable altitude mission. And last was an atmospheric sample return mission, and the small probe and the balloon mission will act as precursors to this atmospheric sample return. Next slide, please. So the balloon mission has 2 primary science goals. The first one is to search for evidence of life in the Venusian clouds, and this is achieved by 4 objectives: by detecting reduced gases and anomalies which can be attributed to life chemistry, and to detect the presence of organic material and identify this organic material, and also detect morphological indicators, that is cell membranes in the cloud layers. The second goal is to measure habitability indicators. So we want to characterize the habitability in a given altitude range. And this is through determining the water vapor and acidity of the cloud, and to detect metals which can support metabolic activities, and also to measure the temperature, pressure, and wind speed to provide a context for other measurements. Next slide, please. The primary flight systems is a launch vehicle that is capable of launching about 1,500 kilograms to Venus, and a Falcon 9 reusable vehicle is very well suited for this. Then there's an orbiter plus cruise vehicle, which will carry the entry system to Venus and also act as a communication relay there. Then a standard 45 degrees sphere cone aeroshell, which will carry all our aerial platform and inflation systems. Then a 12 segment variable altitude mechanical compression balloon. Maxim will be talking, I think, more about the mechanical compression balloon. And for this study, we have baselined 45 to 52 kilometer range for this balloon. And the science gondola is a pressure vessel which is based on the Pioneer probe design. Next slide, please. For the baseline, we have selected a trajectory in 2026, which takes about 150 days to arrive at Venus. And the orbiter and entry probe are launched together. The orbiter acts as a cruise vehicle throughout the interplanetary trajectory and releases the entry probe as it arrives at Venus and then enters into an orbit. We did a trade study for selecting an orbit such that it achieves its primary function as a communication relay. And we baselined a synchronous orbit, which is 5 to 6 days long, based on the circumnavigation time for the balloon. Next slide, please. The entry descent ConOps are derived from the Vega balloon concept and the Vega balloon mission. So the entry interface is at about 180 kilometers, and after the entry probe passes the peak deceleration and peak heat rate regions, the drogue chute is deployed, heat shield is jettisoned, and the aerial platform and inflation systems are released. The inflation begins at about 72 kilometers, and it takes about 5 minutes to reach 50 kilometers. So we have 5 minutes for inflation, and it still descends till 44 kilometers. So we have a few extra minutes for inflation if needed. At 44 kilometers, the inflation system is dropped, and it acts as a ballast, and the balloon rises up. And from 45 kilometers onwards, the operations begin. Next slide, please. So, but from 45 kilometers to 50 kilometers is the control range for the balloon. So to rise up, the balloon is extended, and to descend, the balloon envelope is shrinked. The maximum ascent rate for the balloon currently is about 8 meters per second. So this ascent rate can be controlled based on the desired time in a particular altitude range. It can hold the altitude without any extra power required, and there will be natural variations at that altitude, and we don't require a precise control for a given altitude, so the natural variations are allowed, and as long as we know what altitude we are at. And this the duration of this cycle, the complete cycle, can be controlled based on these ascent and descent rates. And in the mean, all the time, the orbiter is acting as a communication relay. And when the Earth is visible, direct to Earth communication is also used. Next slide, please. So to give an overview of the mass, the total mass is 1500 kilograms with an orbiter of 450 kilograms, which we are thinking of using a CubeSat or a small sat because the primary role is only communication relays, and it doesn't have its own science objectives. And this can also reduce the overall cost. The entry system is about 1,000 kilograms with 500 kilogram of aeroshell and 500 kilograms of descent module. And the floating mass of the variable altitude balloon is about 450 kilograms, including the gondola, which carry about 45 kilograms of science instruments. Next slide, please. So in conclusion, this overall mission, it provides an extended period of exploration. So the baseline design is for 30 days, but it can keep exploring after that because of the balloon materials allows it to be operational or afloat in the cloud for a few months. And this allows for a 3-dimensional plus temporal and day-night profiling of these samples. It explores the it should be the lower haze, lower cloud, and part of the middle cloud layer, and it searches for evidence of life and measure habitability indicators, and also characterize the cloud droplets. So we performed an end-to-end mission architecture utilizing a mechanical compression balloon, which is most of the previous studies have used a pumped helium balloon. So this is a new study in that sense. And the total stacked mass we came up with was about 1,500 kilograms. And there is still scope for more trade studies and optimization, so this could be reduced further. And the balloon mission will also act as a precursor to atmospheric sample return mission by providing cloud droplet characteristics and informing a sample capture and storage techniques, so which will help in the atmospheric sample return possibly by the end of the decade. Thank you for your time, and I'm open for questions.
That's great. Thanks for that excellent presentation. Have we got any questions? Well, perhaps I can start with one. I saw that you're proposing to use an orbiter for your data relay, which is synchronous with the rotation of the balloon. The atmospheric wind speeds are somewhat variable, and so there may be a risk that you get out of phase. Did you look at the robustness of this? I mean, perhaps are you planning to use the vertical wind shear to adjust the speed of the balloon to get back in phase with your orbiter?
So the synchronous orbit is one of the baselines, but we also the problem that you mentioned is we considered that, and there is an alternative that we can use a smaller 6R orbit, and the orientation is the inclination is as low as possible, such that the balloon is visible once every 6 hours. So that is also an alternate possibility.
Okay, thank you for that. If we have no further questions, I suggest we try again. Maxim, are you back online?
So Colin, Max, I talked to Max. He said he was going to call in, but he doesn't seem to have done that yet.
Okay, well, in that case, let's just carry on with the next presentation in the running order, which is by Jose Magallanes. So yeah, Jose, I see from his title slide, he's just finished a BS in Aerospace Engineering from San Jose State. So congratulations, Jose. Over to you.
Good morning, I'm Jose Magallanes. I'm from San Jose State Altitude Cycling Balloon Team. Other members of this team included Katrina Hale, Eric Hahn, Diego Castillo, Tyler Neca, and then our advisor, Dr. Papadopoulos. Next slide, please. Yeah, so quick introduction. As I said, San Jose State, just class of 2021 with my BS in Aerospace Engineering and my minors in math. I'm originally from Fresno. My main areas of interest include aerodynamics, propulsion, CubeSats, manufacturing processes, and test engineering. Next slide. Agenda. We have the project overview. We're going to do the subsystem breakdown, testing, and what we plan to do in the future. Project breakdown. So quick mission statement. We want to develop a modular altitude cycling balloon that can carry payloads of different sizes, capabilities. Our initial testing is taking place here, obviously, but we intend for this to go on to Venus, other missions, and be able to work on different planets using different payloads. We also want to design a system that takes all of our sensor data and would live stream it to us just so we can get everything in a timely manner. Next slide. Yeah, so this is small diagram of our system. You can see at the top there's a top plate with hook. Through it running a Kevlar cord running through a bunch of mylar balloons and our connectors that can be separated to add or remove balloons as needed. All the way to the bottom, it's going to be a mechanical altitude cycling method, so we're using a stepper motor. And all our electronics and sensors are also at the bottom. Next slide, please. Our subsystem breakdown coming up. Yeah, so as you can see, we are like a college team, so we're trying to stay on a budget. We're using a little bit like cheaper balloons. They're still large enough. It's still Mylar, but they run 10 cents a piece. So they were a lot easier and affordable for us to use. On the left-hand side, you can see one of our connectors. This was during our first test, and we ran into the issue of adhesive. We found it's kind of hard to adhere things to Mylar. We were using PLA pieces. Next slide, please. Structures continued. So on the right-hand side, you can see the same picture from the last slide. We changed that to the left where everything's threaded because we're having issues with leaks. And we also add a little bit more surface area at the base to make sure that our adhesives would adhere better to the balloons. We also added Teflon tape between each threaded connector that would make them further airtight. Next slide, please. On the right-hand side was our first design of our electronics and stepper motor bay. On the right picture, you can't really see the stepper motor area because it's attached to the balloon already at this point. But we made everything out of PLA, tried to keep it as light as possible. It was still a bit too heavy, so we went with what's on the left, which is foam core. It was practically double the size, but still half the weight. So it gave us more room to put all our electronic systems more organized and stuff like that. Ideally, in the future, we would have switched to a lightweight PLA. It's a PLA that as it heats up further, like at higher temperatures, it foams up a little bit. So it'll still let you print out same 3D printable pieces, but it'll be half the weight of regular PLA. Next slide. We broke our electronics into two separate subsystems, the first one being all the sensors and the second one being stepper motors. This was mainly done because of COVID. We weren't in the same area at the same time, so it'd been a little bit easier to have separate teams working on separate stuff. The first system of sensors include a BME280, an MPU6050, an XP-S2C as our communication system, and an Arduino as our microcontroller. Second system had an ESP8266 microcontroller, an A4 988 stepper motor driver, and then a NEMA 17 stepper motor. Next slide, please. So our wiring diagrams. You can see on the left-hand side, that's all our sensor information. So there's one BME280 that was inside the balloon to measure internal pressure. A second BME280 that would measure all like the ambient sensor data information we needed. And then an MPU6050 that would just read acceleration and velocity. The right-hand side is the stepper motor controls. We have the ESP8266. The microcontroller connected the stepper driver to the stepper motor. And then in this picture, it's a 9-volt battery. On ours, we had a 12-volt power supply that's wired the same way. Next slide, please. Just a little further in depth on the sensors. The purpose for the sensors was to take atmospheric readings to see if the balloon's at proper operating conditions and to inform us of internal pressure just to make sure we don't pop anything. There's two BME280s. The first one is used to measure atmospheric temperature, pressure, and altitude. Then the second one was used to measure internal balloon pressure. And then MPU6050 was only used to read ascending and descending acceleration, but it also had velocity capabilities and it was a gyroscope. We didn't use that. We didn't need it at the moment, so it allowed us to transfer data faster. We used both of these because they were like really low power consumption, whereas the XP that we were using had a little bit higher one, so we were trying to minimize what we could. The data collection done by the XP was all remote and monitored using Python script. Next slide. Thank you. Our communication system. The first one was a sensors communication. We used an XP-S2C to send and receive all the data. Theoretically, the maximum range would be about 2 kilometers. When we were testing at the rate we were sending data, it was about 600 feet. But that was to receive data like every half second. So we were getting stuff really consistently. It worked really well for all our Earth testing. In the future, we'd have to switch to something different because it wouldn't get that much range. It also allows us to use the Arduino I2C protocol really easily, so we can add sensors as needed. The separate motor was the ESP8266. We used it to communicate through the Blink app. It was pretty easy to program, straightforward, and any phone can get it. We noticed no delay on it when we would send data, and it was just used to rotate the stepper motor. The max range depended on the Wi-Fi connection. In the future, if we're still doing earthbound testing, we'd probably switch to a Bluetooth connector. Next slide. The main softwares using this was Arduino IDE, XCTU, and Python. Arduino IDE was used to gather all the sensor information, just raw data and numbers, to send it through the XP. And we also used it to connect the ESP8266 to the Blink app and to Wi-Fi. XCTU was just used to program the XP to communicate strictly with each other. The main advantage of that was we didn't have to get any permissions to use them, because a lot of other ways of transferring data would use radio frequencies that other local people use as well. The XP, we didn't have that issue. And Python gathered all the Arduino data from the XP and displays it all in live graphs. Next slide. Testing challenges. You can see the balloon's really tall. It was about 25 feet tall, if I recall. The first testing was our fully electronics testing. We want to test the capabilities of all sensors to make sure they were giving us usable data. At first, we were getting messed up temperatures, and we fixed that, and everything else was working fine as well. We also want to test the range on XP, which we got about 600 feet, which was more than what we needed, since our testing is only about 20 feet. Then our balloon structure test, we wanted to find all the leaks we could, as we did with our initial connectors. There were a lot of leaks. Once we fixed that and printed out new pieces, everything was working fine. We also had to increase the number of balloons, because our initial calculations only required 10 balloons, but we realized that was taking into account perfectly spherical balloons, and my balloons aren't perfectly spherical. So we ended up adding more balloons. Then we wanted to test the compression system, which was the stepper motor pulling the cord from the top and increasing the pressure inside the balloon. That all worked. We were able to get about a descent of 15 feet. So we still had it tethered, but we compressed it, increased pressure, and our balloon was descending. Next slide, please. The XP communication system. That was one of our big tests we needed, since this project relied heavily on live data. The first thing we did was create sensor code that would just collect all the data raw, just numbers. Then we connected to XP to the Arduino to receive and send data. Then create a Python code to neatly display all the information. Next slide, please. These are pictures of all the data information being sent. Top left-hand side, current altitude, then temperature, pressure, and acceleration. You can see we were testing temperature on this one. Someone put their thumb on the temperature sensor, and we can see the temperature increasing, so we knew everything on that was working fine. Same with the altitude. We adjusted it for actual height of San Jose, the area we're testing in general, not from zero, not from sea level. The pressure was around zero. It was fluctuating a little bit, but nothing too big. And the acceleration, the Z was moving just because we were moving the balloon a little bit. Next slide, please. Stepper motor controllability. We were using a pretty small stepper motor. The initial test had no response, but just faulty wires and soldering problems, which were easy to fix. Once fixed, everything worked fine. The stepper motor pulled the cord and released the cord as needed. The only issue we ran into here was the stepper motor was heating up a little bit more than expected. And anyone who worked with PLA parts know they have a pretty low temperature threshold for malleability, which is why they're okay for earth testing, but not good if you're actually going to go somewhere with them. So everything was warping with it, the case it was held in, so it would affect the angle of it a little bit, but besides that, it worked fine. Next slide. Challenges. Some of our main challenges were working remotely. Everyone had to deal with COVID. It was a little bit hard on the senior project because school was closed and we all lived in different areas, so we couldn't really meet. Our funding was a bit of a challenge as well. We had to go with the cheaper mylar balloons we can find. They were about 36 inches, which is pretty small for this project. Ideally, we want bigger balloons, which also leads into how hard it was to manage a 25-foot structure of balloons. Any wind would kind of alter like the way the balloons are standing, and it would kind of mess it up. Bigger balloons, wider balloons would be a little bit easier to handle than a really tall, thin structure. There was also issues identifying the first set of leaks. It ended up being the thread, the connectors at the base was threaded as well, where there were a lot of leaks. Limiting weight too. A lot of our materials were kind of higher weight. PLA is not super heavy, but for it to be airtight, it is a bit heavy. Then integrating CAD's balloon electronics, just because some people had some parts working remotely, so we can all connect at the same time. And when we did, it'd be like a far drive. We'd connect them, then we'd have to go back home, redesign, print parts. Next slide, please. Future work. Ideally, we'd want to manufacture our own custom balloons in the future. We did look into other places to get them, but the cost was a lot higher, so we'd want to try to make our own balloons, make them a lot wider. This would reduce weight by reducing the amount of connectors needed to achieve the same volume of helium, because less balloons, less connectors. We also want to add horizontal propulsion, just so that we get a little more control. Instead of controlling just altitude, we want to be able to at least control a little bit of X and Y axes. Use more lightweight filaments. Knowing more about them now and being able to order them ahead of time, we'd be able to accommodate for those. It cut our weight by a lot, and it let us use 3D printing still instead of the foam core design. CubeSat payload. There was other people at San Jose State working on CubeSats, whereas our balloon was just focusing on the balloon. We'd like to add some of their payloads to this balloon to make it a little bit more capable and add better features to it. And we want to make a PCB for electronics, just to make everything a little neater there. Next slide. Yeah, so I ran through that kind of quick because I know we're short on time. But if you have any questions, here's all my contact information. There's my email, josemarianes@sjc.edu. My LinkedIn. Feel free to contact me with anything if you don't have any questions to ask at this moment. Thank you for your time.
Thank you, Jose. That was great. Not seeing if anyone has any questions, quick questions, put them in the chat. I guess I might as well just say that you've tempted us with this beautiful picture of real kit, and then we were thinking that we'd see some flight data. So is there any chance you'll still get some flight data out of this project, or have you all gone your separate ways now, and is that it?
No, ideally we want to keep working on it. I know I'm gonna try to, because senior projects kind of people might leave them in the past, but I did enjoy working on opposite cycling balloons a lot, and I like to see it go into like further like directions. So I'm going to be contacting next year's team to like try to get more things about it and do further work on it. I think we made good progress for a year and starting from scratch, but I do want to see more done with it. So I do want to keep working on this.
Great, very exciting project. I think in the interest of time, let's carry on. So I understand that Maxim is back and now connected by phone. Max, are you there? Calling Maxim de Jong. Third chance. Max, are you there?
Hear me now?
Yes, we can. Excellent.
Wow. Fails.
So great. Why don't you start your talk then?
Okay, I'll get on with it. My sincere apologies. It's bizarre. I just got off another FedEx or another call using the same platform just before this, and it worked absolutely fine. At any rate, extended range altitude control balloon for Venus. Next slide, please. The idea of extended altitude range is particularly attractive. The preceding talks went over that in great detail, what the best science benefit would be. As you've already been identified with in previous talks, the main issue, one of the main issues that was introduced was density. So you need to have a balloon platform that can accommodate the difference in density with the different altitudes. And more about that in a following slide. But for the time being, when it comes to the other aspect, and this is what this talk focuses primarily on, the issue of temperature. At the upper range, of science interest, 60 kilometers or higher, We could go all the way to 75 kilometers and it wouldn't be a problem because with temperature, because we already know how these materials handle. They've been developed terrestrially for stratospheric application. The problem comes if we want to dip below the cloud layer and the temperature in those areas gets well over 100 C. We've been developing materials that are, that'll be palatable or useful in the range of about 145 C. Next slide, please. The altitude control platform, of course, that we've been working on for a number of years is mechanical compression altitude control balloon. These balloons that you see on this slide are all different balloons that have been built and flown terrestrially. There's a couple of balloon systems going to the North Pole this fall, so we are starting to rack up a fair bit of flight experience with these units. It's sort of like an accordion. It can accommodate the difference in pressure with great altitude range. Next slide, please. Quick introduction to how our architecture works or why we've chosen it the way it is. It's a proprietary design, and one of the big challenges with anything inflatable, deployable, and so on and so forth is that you really need to be able to build it, and you need to be able to build it with the materials that you need for the final application. So we have a design premise here. Unlike the Vega balloon that is made out of a material that's thick enough and strong enough to withstand the requirements of the particular mission, if we want to do something more advanced, larger systems, larger balloons, we need to segregate material, functionality. So if you're trying to maintain a pressurization for altitude control, regardless of the system you're using, you're going to need some element of the balloon being super pressurized. We're segregating the pressure restraining structure, which in our case is a system of tendons. We're segregating that from ultra-high performance gas barrier. And because the gas barrier, we want to really focus on making it as lightweight as possible and yet be very, very, very efficient. So we've segregated pressure restraint capabilities, as we see in the top right, a gas barrier laminate that's optimized for highest reliability gas barrier and highest performance, and then an exterior fluoropolymer cloak protecting against acid. Next slide. Okay, when it comes to our particular architecture that we're using, it's a patented system, and one of the huge benefits from our point of view, having gone through deployable, inflatable structures for the last, few decades, including the Bigelow habitats that were, Genesis 1 and 2 that were launched, we really need to have predictable and reproducible assembly systems. So when it comes to the gas barrier, for example, we like to have planar seams. We want to stay away from a gore-based construction, as you see in the top right-hand corner. The Vega balloon image on the top right-hand corner, you could see where the panels, like an orange peel, join together, and you could see puckers and so on and so forth. And this is highly problematic once you start wanting to go to really specialized materials, especially for high temperature. Next slide. So when it comes to developing materials, which is really was the focus of this particular, project, since we already have the architectural capabilities and we have the flight capabilities and so on, we're wanting to go below the cloud deck. So to be able to combine all the requirements into one product for gas barrier, as we see in the middle here, task, where it says task, we're after sort of an elusive combination. It's sort of like a Rubik's Cube. Everything's vying for design supremacy. So we need to have superlative barrier performance. We need to have, acceptable strength, at least for the local shell loads, where we have those lobes between the tendons. It has to be, very resilient, for deployment and fabrication, mission-related abuses. Of course, elevated temperature survivability. And you have to be able to build the balloon out of a gas-tight seaming, integration with subsystems, and so on and so forth. At the bottom left, we see critical considerations. It's really important to realize when we go up to about 135 C below the cloud deck, you get like a 120-fold increase in barrier gas transmission. So you need to have a very, very high performance gas barrier if you want to have an extended mission profile. The other thing to remember when you're designing, you think, well, we could just make this thicker and we can take a mass hit if we make the balloon a bit bigger. But if you get into thicker materials and you have to join them together and you have to integrate them, you have a very much reduced structural predictability. And everything that we know, we'd like to consider ourselves being on the cutting edge of inflatables and deployables and fabric structures, is what we really want is predictability, structural predictability, and reproducibility. Next slide, please. So in this particular project, we really, went well beyond what any type of budgetary limitation we initially had, because it was a fascinating project and it was something we really wanted to investigate while we were really, while we had all these materials in hand. So we got a lot of custom-made laminates. And there's a whole list of components that we used as building blocks in these laminates to investigate, okay, what can we come up with this Rubik's Cube of design that will fulfill all these requirements? And we came up with a couple of very promising, candidates, and we came up with a lot of candidates that were very, very unpromising, as always happens. You could see a variety of tests. We ran hundreds and hundreds of tests, literally, on the raw materials in a variety of scenarios involving high temperature, high loads, and so on and so forth. If we look at the next slide, what you see here is three primary objectives. We want to characterize and assess the permeability, compromising trauma mechanisms. So whatever mechanisms that compromise the permeability. So, if you're folding, deploying, wrinkling, pressurization, temperature, so on and so forth. Then we want to do a pressure decay evaluation of the degree of trauma that we've inflicted. How does that, if we inflict trauma, we pinhole, let's say, what type of resistance do these materials have? And thirdly, we really want to develop a trauma assessment tool and methodology so that we could say, okay, well, we can really predict what's going to happen, and we can actually quantify, what these effects are going to do to the particular barrier film. So we developed our own code for density of pinholing. It's a great example on the bottom left. The size of pinholes if we've repeatedly wrinkled the material, and as you'll see in this slide, the baseline originally was going over 100 or 1,000 to 2,000 pressurization cycles, pressurization up to the levels of what an actual Venus balloon would sustain, and analyzing what type of trauma we could impart if something is heavily creased. There's all kinds of different crease configurations that you want to investigate, but of course we wanted to narrow it to what an actual Venus balloon would endure. The test setup is shown on the right. We used UV backlighting to detect what type of trauma and pinholing there might be. So a very involved program in this regard. If we move to the next slide, you'll see where the attention really gets focused on the actual balloon application. And these are, it looks simple. These are basically, barrier film sausages that were inflicting a lot of, trauma and a lot of problematic scenarios that would be representative of an actual mission application. These are very difficult tests to run, as simple as they look, because we want to get the shell, the entire structure, up to a high temperature, which means you have to have hot air inflating and insulation to make sure that the heat is evenly distributed throughout the thickness of the material. We imparted different tendon thicknesses or tendon tensions to it to really wrinkle the material, to really show, okay, in a worst-case scenario, this is what's going to happen to the balloon film if we compress it. And then we also compressed at high temperature as well. In the top right, you can see that. And then, of course, the critical thing, you can have the best material in the world, but unless you have a method of integrating it, integrating seams and so on and so forth, you're still nowhere, basically. The seams are absolutely crucial, and they have to survive very similar conditions that the actual balloon film does. So this is a really cool slide from my point of view because it brings back memories of weeks of running these tests and fine-tuning, and that really quickly narrowed the playing field of candidate materials. Then the last phase, if we go to the next slide, was to come up with, okay, it is a subscale, but we want to, build a high-fidelity demonstrator that we can actually, cycle at pressures that exceed what we would normally see in a balloon and traumatize it, go through dozens and dozens of cycles, and then do a pressure decay test. And the following slide shows the test setup that we had for that, which is very interesting. They're all very interesting if you like what you're doing, right? So in this particular test setup, it really demonstrates how powerful inflatable structures can be, and we obviously have a lot of experience making these things, but it really hits home when you have like a test article that's a 1.5 meter diameter. It has PBO tendons. It's gossamer. It's like a child's balloon, and yet the steel plate that's balanced on top of this test article weighs about it's well over half a ton, so 1,200 pounds. And so what we're doing is inflating this balloon segment, and we're letting the weight, compress the balloon. So we're lifting this 1,200-pound steel mass up and down just with inflation pressure. And, of course, our desire is to impart a very significant amount of trauma that would exceed what we would see in normal compression cycles for a Venus balloon, after which we would do the pressure decay test. We have data from all these tests. Ultimately, we had a candidate film that's a little bit on the heavy side, but it's still it's a hanger queen at the moment. It's about 7 months that it's been, hanging from the rafters of the high bay facility here, and it hasn't had a very appreciable pressure loss, so we're very happy with that. This is ongoing work. We have a current contract that is going to continue for the next couple of years in fine-tuning this and bringing it to a full-scale level, including developing deployment tactics and so on and so forth. I really appreciate your patience in this regard. I want to thank my co-authors, and especially Jim Cutts for his eternal enthusiasm for everything that we happen to be doing at Thin Red Line, and great thanks in that regard. You can go to the last slide because I think it's really attractive. That's the primary test article that's still surviving at Thin Red Line currently. I'd love to answer any questions if there is any time left.
Great, thanks for that excellent presentation, Max, and for sticking with the audio problems and so on. Can anyone put any questions in the chat window? In the meantime, let me just ask, you're operating down at higher temperatures than some of the other balloon technologies we've seen. Is that an inherent advantage of your technology, in that it doesn't have the sewn, the gores and so on? And what is the limiting factor which controls the temperatures you can go up to? Is it the sort of the mid panel failure, or is it something else?
That's a great question. That really cuts to the chase. JPL's been doing a fantastic job. Jacob's presentation really showed what they were doing when it came to the pumped compression. The niche that we were carving out and that we were very, very interested in was elevated temperature. So the primary challenges are regarding integration, like seaming. To have something reproducible that will, handle high temperatures, the idea of staying away from gores to us is crucially important. So, again, you can have the best materials in the world. If you can't fabricate something that has joints that are commensurate to the innate abilities of the material, then you're behind the curve, and that's a very dangerous place to start in a developmental sequence. When it comes to being able to go lower, to lower temperature, we're trying to leverage as much off-the-shelf insight and building blocks, and then we're recombining them in a custom sense to be able to have continuous operational capability at like 135 to 145C. We can use those same methodologies and incorporate different building blocks, but that would be more costly and more time consuming. But we are able to get down, from our point of view, we're able to get down to, below the 40-kilometer range with a different set of materials. Easier said than done, but we'd like to use an architecture that we presented here that would be a viable candidate to be able to accommodate the materials and the fabrication capabilities to get down to those lower altitudes. We can also go lower. We've experimented with annealed steel. That was a concept that was introduced by JPL quite a while back to go very, very low. And we're thinking, okay, with our system, we can have planar seams and we can have a bellows structure using the same type of architecture, but switching to annealed steel, as the barrier membrane.
Excellent, thanks for that. I'll note that there's a couple more questions for you in the chat window, but in the interest of time, let's move on for now, and perhaps if we have any discussion time left at the end of the session, we can come back to them. Before I move on to the third part of the session, which Jim will chair again, I'll just bring your attention to two poster presentations, which are assigned to this part. One is Bridging the Gap Between Aerobots and Landers for Venus from Gilles Bellet. And the other one is Aerial Platform System Design for Finding Life at Venus from Weston Buchanan. You will find certainly video summaries of those on the IPPW Venus Exploration webpage. Please do have a look at those. And with that, I'll hand back over to you, Jim Cutts, for the third session.
Okay, Colin, so let's move smoothly and quickly into the first presentation of this session. This is going to be Siddharth Krishnamurthy, who's a research technologist in the ionospheric and atmospheric remote sensing group at JPL. And he works on instrumentation and technology development for Venus exploration. He also happens to be the chair of the student organizing committee for IPPW. So, Sid, take it away.
Thank you, Jim. And perhaps from the background, you can tell that I am sitting a few feet away from Jacob at Near Space Corporation, testing Venus balloons this week. So when I'm not playing with balloons with Jacob, I'm playing with balloons with other people, and they're all listed here. So acknowledgement to all my co-authors. If you could go to the next slide. So what I want to talk to you today about is the possibility of exploring Venus' seismicity using balloon-borne networks. And here's an outline of my talk. So I'll just give you a little bit of background and motivation. I think Paul's done an excellent job of already doing that, so I won't be spending too much time on it. But I'll introduce infrasound seismology to you, and then also briefly present a balloon network study that we did on Venus at JPL a few months ago. Unfortunately, because I don't have a lot of time, I'll only be hitting the highlights, and then if you want the details, we can have a conversation afterwards. Next slide, please. So in terms of interior and seismicity, Paul has already demonstrated this quite beautifully, I think, in his lovely pictures. But Venus has its own distinctive tectonic and volcanic character. You see several landforms on Venus's surface that indicate volcanic structures or seismic strain. That crustal belt at the bottom, the third figure there, Paul's already shown it in false color, and it clearly shows signs of seismic strain. And some of these might actually be ongoing. In terms of estimates, Venus is thought to be seismically active somewhere between the level of Mars and Earth, but that range is very large, primarily because we have not ever made a direct measurement of seismicity on Venus. And there's good reason for that. As mentioned before, surface conditions are very harsh, and anything we've landed on the surface has not lasted for more than 2 to 3 hours. And that is much too short to measure any kind of seismic activity. Next slide, please. So this is where balloons come in, because they can float at 50 to 60 kilometers where the conditions are far more clement, and then we can get much longer lifetimes. And this idea for performing seismology or detecting seismic activity, both in terms of quakes and Venus volcanic eruptions, primarily relies on the coupling between the solid planet and its atmosphere. So when the ground shakes or some energy is injected into the atmosphere, it produces acoustic waves that travel a fairly large distance from the originating event. And the coupling is actually 60 times better on Venus than on Earth because the atmosphere is so thick. And primarily for quakes, we are interested in two kinds of, sorry, I should mention, the low frequency component of this is actually called infrasound, which is the opposite of ultrasound, and it travels a fairly long distance. And we're typically interested for quakes in two kinds of infrasound. So one kind is generated directly above the source and travels directly to the balloon from there, and it's called epicentral infrasound. But sometimes seismic activity may also set up surface waves that travel through the crust of the planet, and then that produces infrasound as well, which travels vertically upwards, and that's called surface wave infrasound. One other advantage of doing this from balloons is that you can easily in quotes, deploy several balloons from a single aeroshell, and they can naturally separate in the atmosphere. So you actually have a network deployment that's possible from a single aeroshell. Can we go to the next slide, please? So we've been doing a lot of work on this on Earth. I primarily focus on the earthquake side of things, but there are other groups who work on the volcanic side as well. In 2018 and 2019, we did some experiments with artificial seismic sources, such as a seismic hammer, to show airborne infrasound detection and geolocation from a short range. Partners in France recently showed short-range seismic detections using underground chemical explosions. But I think the big ticket result that came out recently, actually just about a month ago, is when we showed the first demonstration of a natural earthquake from a balloon that was at 4.8 kilometers altitude and about 80 kilometers away from magnitude 4 quake. This plot that you see on the right is from that recently published paper. The balloon's name was Tortoise, and in this square region, that shows the actual detection of the acoustic wave from a surface wave generated by this earthquake. The details are in the paper, so I would encourage you to go read that. In terms of volcanoes, we have another group that studied eruptions from a Strombolian erupting volcano called Yasur volcano in Vanuatu from a tethered balloon. But that's still early days on that study, and so some work needs to be done there as well. Next slide, please. So the next big step in this activity is actually ongoing right now. These are photos from just 2 weeks ago. We have started a campaign called the Balloon-Based Acoustic Seismology Study. It's funded by the NASA P-STAR program. And it involves several overflights of the seismogenic zone in Oklahoma in the US by Oklahoma State University students. These two pictures that you see are actually from the very first two launches, and they've worked themselves up to 10 launches now. And we plan to go to about 30 to 40 launches over the next 5 to 6 weeks. This plot that you see is from the first day, showing the trajectory of the balloon after launch, and all the stars are earthquakes that happened while the balloon was in flight. Our main aim is to collect as many earthquake signatures as possible and try and understand the detection limit of this technique, and then extrapolate those results to Venus. Another thing of interest here is to examine schemes that would allow for automated detection of earthquakes in the infrasound record. Because on Venus, we don't have ground truth, and so that's an important part of developing this technology, is to be able to recognize an earthquake or Venus quake signature or a Venus volcanic eruption signature when you see it. So far, quite like InSight, we have not been blessed with a somewhat large quake in the balloon path. So they've mostly been in the 1.5 to 2 range, but it does give us good data to explore the lower limits of our detection scheme. Next slide, please. So in terms of detection modes, we have two. So traditionally, we have flown two barometers on a tether, and what that allows you to do is to do differential measurements and measure time of flight with a known distance between the two packages, and be able to infer directional information about the incoming signal. But we're also working on something we call vector infrasound, or aeroseismometer, interchangeably depending on who you ask, where if you measure not just the pressure, but the balloon's vector response to the pressure using an inertial measurement unit, you can actually determine some kind of directional information from that measurement. So we initially did experiments here in 2018 in JPL at a very short range, but in 2020, our partners at Sandia flew a balloon to 20 kilometers altitude and conducted 3 separate explosions at where it says source in that plot on the right. And 1, 2, and 3 were the positions of the balloon. And we did this kind of vector measurement and tried to invert for direction. And those blue cones show the direction inverted. And you can see it does actually a pretty reasonable job of being able to track back to the source. And so the main advantage of doing this is that it eases the deployment complexity. So you don't have to deploy a tether, and like a single system, single station can give you directional information as well. Next slide, please. So switching directions a little bit, we sort of tried to put this all together and tried to do a study where we deployed a network of balloons on Venus in simulation. And our objective was primarily to study whether altitude control and onboard autonomy and a reconfigurable balloon network can increase the science return from a balloon-based mission on Venus. This was targeted primarily towards performing high-value science. So we geared this towards a volcanic eruption. So what we were trying to study was, if we detect a volcanic eruption, can we get close to it and perform some high-value science, like dropping a sonde or taking a picture or something like that. The one thing I will mention is that for this kind of network reconfigurability, a good knowledge of wind fields is a prerequisite. We use the IPSL model in our study, but really this sort of network reconfigurability is something of a second generation technology, because we would need to know the winds on Venus pretty well to do this planning. Next slide, please. So just a little bit about the architecture on this study. We had a single orbiter and 3 variable altitude balloons, and these can be pretty small, and these can either be the pumped helium or the mechanical compression aerobot. We're pretty agnostic to how the altitude is changed. Each balloon we assumed was able to detect infrasound from volcanic eruptions and float for about 60 Earth days. And we added an orbiter that was a communication relay platform, which was in an equatorial circular orbit at 30,000 kilometers. So it had basically half the planet in view at any time. And so we assume that the balloons can carry a high value experiment. So you can go up close within 50 kilometers to visit an event and say drop a sonde through an erupting plume, or like take an image immediately after an eruption happens. And we also assume that all elements of the network can communicate with each other with some restrictions on that. The volcanic activity was with the lack of information was assumed to be the same level as the Earth, but we're also experimenting with other levels of activity. Next slide, please. So this is a brief summary. There's a lot more to say here, but I don't have the time. But we did Monte Carlo runs. So far we completed 100 independent runs. We're actually ramping up the size of this. But over these 100 independent runs, what we found was that the onboard autonomy guarantees at least one up-close pass, which is a very high science value. And also reduces the median time of the close-up visit after the event has occurred, and also has more total up-close visits per detection than having no autonomy where the balloons just float around. So in this video that's playing on the right, what you see is those magenta lines. So the square is the orbiter going around the planet, and the 3 blue circles are the balloons. Every time you see a magenta line pop up, the balloons and orbiters are communicating. So, and the events are the stars that show up periodically, and the stars change color according to that legend. So what you're seeing there is that the balloons are able to solve a Markov decision process problem where they're only made aware of the statistics of the wind, and they're able to change their altitude to target flying over this event as it happens. And so there's a lot more.
Sid, you're breaking up. Can you get closer to your phone? Yes, that's better.
Okay.
Yeah, much better.
So the punchline to repeat, punchline being that autonomy and altitude control can bring you a much more high value science here than like not having that kind of control. Next slide, please. So in conclusion, so the few things that I want to leave you with is, one is that we've shown that seismic infrasound from quakes and volcanic eruptions is detectable from balloons. We're obviously studying the levels of detection and how to distinguish the signal from the background. We do need more instances of seismic events for this, and we are our campaign is primarily geared towards collecting all this data and trying to perform this kind of Bayesian analysis. And the other is the fact that agile and reconfigurable networks can be deployed with relative ease compared to lander networks on Venus, and that onboard autonomy on these balloon networks can enable better triangulation of events. So if multiple balloons detect the same event, that's always a great thing. And also perform high value science with a faster response time by flying closer to the event and having a closer look. So I think that's my last slide. If we can go one more, I think that's yeah, all right. So I think I'm open for questions if there is time. Thank you.
Okay, Sid, I don't see any questions on the chat, but I have one. So you talked about a mission here, which was really designed to study seismology, a sort of dedicated mission similar to InSight. But likely the first aerial mission will be one that's more like the one that Colin described earlier, which would be a single balloon with a lot of other instruments. What do you think you could learn from the standpoint of measurements on that mission that would be useful for planning the future mission?
So two things. One is that even on a single mission, so while the sort of study that I presented was primarily geared only towards seismology, there is nothing that says you cannot detect infrasound from a single balloon. So even a single balloon flying around would be able to pick up infrasound from these events happening on the surface. And also, the information that we are collecting for infrasound is primarily atmospheric information. So it has a lot of overlap with the atmospheric science goals that Colin presented earlier. So you are measuring atmospheric pressure, and also to disambiguate this information, you are measuring winds, you are measuring balloon motion. So all of these put together produce a wealth of atmospheric information as well. So in a sense, it is both a seismically oriented study, but also a study that's important for atmospheric science.
Okay, thank you, Sid. So if there are any other questions for Sid, put them in the chat and we will address them at the end of the session. Now, discussing the end of the session, it's been brought up that partly because of our technical problems today, partly because of maybe we just didn't have enough time allocated anyway, we are giving short shrift to the posted presentation. So what we're going to do here is to extend the time at the end of the session. So for those who can stay on, and hopefully those will be the posted presenters in this session, they'll have an opportunity, a more extended opportunity to get questions. So that's the plan. Now we'll go on to the next presentation, and that's by Kevin Baines, who is a principal scientist at JPL and also a senior scientist at the Space Science and Engineering Center at the University of Wisconsin-Madison. Kevin specializes in the composition, cloud structures, and dynamics of planetary atmospheres, particularly of Venus and the Jovian planets. And he's participated as a PI or project scientist on, wait for this, 8 Discovery and New Frontiers proposals to Venus, including 3 involving long-duration globe-circling balloon platforms. So nobody, I think, knows more about this topic than Kevin, and Kevin's going to talk about measurements in the subcloud region using balloons. Kevin?
Okay, thank you. Yeah, thank you, Jim, for that great introduction. Yes, so today we're going to talk about our ability to go image the surface of Venus from below the cloud layer. And as Paul summarized very excellently, it's really valuable to do that. On this slide, you see basically a radar image of Venus, a global view, but it's obscured by those clouds in the bottom image, and those clouds act like a frosted glass. and it diffuses the light. So any light that you get from the surface of Venus gets diffused and spread out and scrambled. So the best we can do is about 50-kilometer resolution. That's 50-kilometer resolution from orbit using the infrared techniques. And we're talking here about the technique that was basically honed in the 90s, and when it was discovered that you can actually see the surface of Venus in Venus's own thermal glow. It's glowing like an oven, and it puts out radiation, and except for the clouds blocking it and scrambling it, you'd have a great view of Venus's surface using that its own thermal glow. And then the infrared, as was mentioned, there is 5 different windows you can use between 0.85 and 1.2 microns that allows you to see surface materials at 5 different wavelengths, so you can get a spectrum of the surface there, and you can start analyzing the composition. And the composition is important, as Paul alluded to, because of different geological processes, but also because of weathering. Chemical weathering on the surface of Venus basically changes substances. I call it alchemy on the surface. You get different types of sulfur-bearing ions that basically change from one form to another as it releases sulfur in the atmosphere or absorbs sulfur. So you can get an idea of weathering, and that weathering then gives you an idea of the age of the surface. So we can, down the road, we hope to be able to tell, old lava flows from new lava flows, and be able to constrain that. And in fact, there has been a paper on that we'll talk about in a minute. Okay, next slide. So this shows, again, just sort of a panoply of different types of features on the surface to show that, yes, you can see things. There's interesting stuff below a kilometer scale, as Paul talked about. So I'm not going to go over most of this, but you see different features, different colorings, different types of sizes. On the bottom one there, you even have your bright ejecta patterns coming out from where it gets an asteroid hit, or making the crater. Sometimes you get bright patterns, sometimes you get dark patterns, and you just get all these complex features all over the place. So you'd like to be able to do better than 100-kilometer or 50-kilometer resolution, be able to tell what's going on here, and get it at its composition. Okay, next slide, please. And if you go on down to the surface, you see that you have some, you get closer, you have this volcano here. This is a radar image on the top, and then below, they did the best they could with the Vertis images of the surface, and Seuss McGar wrote a landmark paper on this, which even though it was only 50-kilometer resolution or so, 50-kilometer resolution or so, we could kind of tell the different compositions. Some compositions will vary really to that volcano, and she was able to say that this is a geologically young volcanic structure. We don't know exactly how old, but definitely as Paul says, the heart of Venus is still beating. We got geology going on, and this tells us that, yes, there's a good prospect that if we were to get there, we'd see that Venus is alive geologically. And we kind of know that, by the way, because of the clouds. If there were no clouds on Venus, calculations show that those clouds would disappear in about 10 or 20 million or 30 million years, something, geologically young. And so therefore, the fact that there's clouds on Venus is a good connection that says, hey, there's geology on the surface. So from anybody from Earth looking at Venus can tell by the bright clouds there that make it the brightest object in the sky, except for the sun and the moon, that, hey, that planet's got to be geologically active to have those sulfuric acid clouds there. Okay, next slide. And then if you get to the surface, and there was a color image, I think Paul might have mentioned this before, Venera 13 took a color image. This is a color image. The clouds above it are kind of enhanced. Those are artist impressions, but that's the actual surface imagery as analyzed. And you can see a whole host of different types of features there, different sizes of rocks and dirt, and you have flagstone features in the distance. You see more flat areas, and then you have the hills. So there's objects of all different types of scales here, and each of these things may be different, have different compositions and things that you want to study. I stuck in this image at the bottom as a sky view. What you get at this function of altitude as you descend through the skies, and as you get to the surface, it gets very orangey. And so this is real, and that means that if you're on the surface just kind of taking spectra without any help from a light lamp or anything, it'd be hard to interpret it, because you do have orangey color. If you could do things in the visual, it's just everything's tinged with this beautiful kind of orange coloring, but it changes with altitude, as shown in those other pictures. All right, let's go on to the next slide. And so if you had these different wavelengths, what could you do? So I'll just show you one aspect of what we could do. So I had 3 of the main bands there. These are the ones that we find are the easiest to use, so we might as well concentrate on those 3 bands. And then we have emissivity spectra that Jorn Helbert published, Johan Helbert published on here, showing different kinds of types of materials. And the top is sort of a group of different types of basalts, but even amongst them, there are different spectral features as the lines go up and down depending across those different types, those different wavelengths. And then there's a distinct different group down below, some more granitic types of features. So that'd be easy to distinguish. So the question is, how well can you distinguish those things? And I will show you in a second how well we think we could do that. But there's really good compositional information here that we could do. All right, next slide, please. And so Anthony Davis at JPL has this is a really good expert radio transfer theorist, and he's got programs, Monte Carlo programs that we've been using to really see what happens when you have emission from the surface. You have photons coming from the surface at nighttime, so you don't have the background glare. I'll just mention that background glare really dominates everything. You can't do this at all from on daylight. It just swamped completely. You need to be below at least 5 kilometers to get a good view of Venus in the daytime conditions. But from altitude, you could do well, and you just have photons of light coming out, bouncing around with Rayleigh scattering, a lot of Rayleigh scattering. And that's basically the main reason why it's so orangey down there. It's Rayleigh scattering that's going on, getting rid of the blue light. So you have Rayleigh scattering in the infrared as well, not as strong, but you have a lot. So the photons are coming up and getting to your detector, but there are a lot of them being scattered around. So here's an image that of where the light comes from at your detector when you measure something. And on the left, I have a rectangular box, and there's a big DC sort of a delta function there. So, and you can see the scale down there. It says it's about 10 meters. So even less than that. We didn't put it on a finer scale here, but the most of the light, or a good chunk of the light, comes from the first 10 meters of your pixel. Then over the next 100 kilometers, that's where you get the rest of the light. So it's a big AC signal on top of a big sort of a DC flat background that's scrambling up light from all over the place. But you'll see this delta function on top of that when you take an image. So all you just have to do is take enough data that you can cut out that background DC level, and you would see these features. And these are different wavelengths. So the most useful one, the most easiest one, is 1.18 microns. At the top one there, about half the light is in that first 10 meters. And then the rest of it comes from 100, everything out to 100 kilometers. And you notice actually not much additional comes until you get beyond the several kilometers. You got to get 4 or 5 kilometers out there. You can get that curve to go up a little bit. So almost all of it's coming from the 10 meter place. And then a lot of it comes from the big annuluses around you that are way out there at tens of kilometers away. But we can distinguish against that because of the delta function. So we think we have pretty good 10 to 20 meter resolution in here, easy. And this is a Rayleigh, this calculation is for Rayleigh only. So I'll show you one in a minute for when you add a subcloud haze into the system. But this is very encouraging when we saw this. Let's go to the next slide, please. And so then we decided, well, let's go. That was the nice ideal way of doing it, assuming it's completely clear, which the 0th order people, think it's pretty clear below 47 kilometers. So here we used the canonical Nolenberg and Hutton profiles. As you've seen this figure millions of times. It's probably the most shown figure in atmospheric science on Venus. So anyway, these are profiles. Well, it's one profile, but showing 3 different quantities: the number density, the extinction coefficient, and then the mass loading as a function of altitude from up high, I forget how high it goes, 70 kilometers. But you see there's that lower cloud deck, right, around 50 kilometers, extends way to the right. That's a very thick thing. That's the thing that's producing most of the problem. It's optically thick, but it's physically thin. It's only 1 kilometer or 2 across. So you need to get down below that. So really 47 kilometers is the key. You need to get to 47 kilometers, which is about 100 degrees Celsius. And you need to get there. And from there, you just have a lot less extinction. It's way down, factor of 100 or more from what it is above. And so we've done some calculations now about what the visibility of the surface would be and what our resolution would be from that vantage point at 47 kilometers. And off to the left, I kind of show the 2 red lines, you can kind of average over that lower portion of the curve, and it all kind of bounces around that line there, which gives you a certain amount of extinction per kilometer, which is 0.003 per kilometer. And then you have the one to the right, and that's the upper 2 kilometers of that lower haze, the very near to the spacecraft or near to your camera, and that is that produces about 10 times more per kilometer. So you add those two together and you get about roughly 0.1. We think it's a little bit less than 0.1, but about 0.1 extinction, which is not a fearsome thing to worry about. So 0.1 optical depths at 1 micron according to this Nolenberg and Hutton profile. Now, other spacecraft have hinted that it might be thicker at times. So we've done analysis where we come up with this new unit called the KH, or Nolenberg-Hutton unit. So we've gone to 3 times KHs and 10 KHs and 30 KHs to show what happens, which means you have about 0.3 or 1.0 or 3.0 opacities. So next figure, please, and we'll show you what happens when you have that. So this one here is this is the effective subcloud, and we show the different ones. The black curve is for 1 kH, green one is for 3 kH, and red is for 10 kH. And what happens? And these are still, even when you get up to 10 kH, which is about 1 optical depth, you can still distinguish it. And so there's no real change. You still have this delta function. You've got the fall off that still takes tens of kilometers to really be significant. And so you still can see the surface very well below that. Okay, let's go to the next slide. And then we've also looked at, well, let's say that, we don't just use an albedo of 1.0 for all the particles, because the subcloud particles might be made of different stuff. It might have some single scattering albedos that's not conservative, might be about 0.9. So we just took 0.9 as an example, which is actually pretty extreme. And you can see these different curves here. Now, so you see these different curves here. Now here you look at the middle. This case, we're looking at the surface contrast as you have this is called a Heaviside figure. So on the left, the emissivity of the surface is assumed to be 0 to the left of that middle line, and then it abruptly changes to 1.0. So that's your surface that you're looking at. And this is how we'd see the surface through this cloud or this haze with different amounts of KHs on the left, and then on the right, we actually used one KH where we kind of changed the single scattering albedo. But you can see that we still have this contrast right at the 0 line. It still jumps up, so we still see the features pretty well, and it's smeared out a little bit, but not very dramatically at all. So we think we have a good instrument here that will definitely see contrast between different types of features on the surface, and it's not really that affected by single scattering albedo on the right. The blue curves is 0.9 single scattering albedo for the cloud, and then the black is 1.0, and you still have the delta. You have still the same kind of size of a delta function. So therefore, we'd be able to see the surface pretty well. So okay, next slide, please. And so we're designing a camera to do this. And we have 2 styles of camera for our tow body to the left, which, by the way, stay around for the next talk, because Pat McGarry is going to talk about exactly how the mechanics of the actual tow body works. But we're just talking here about the camera and how we can see the surface. And because the tow body is being dragged through the air, from the balloon, it's going to be pointed in the wind. There's a relative wind on the tow body that we can use to keep it pointed. And so therefore, that means we can use a sort of what do you call a broomstick, a broom kind of camera, where you can do different parts of the spectrum successively on one detector. So that's what we're going to do. We're going to do one detector there. You see it there in the middle there, 4 different segments on it. That's 3 different wavelengths. As I showed you, there were 3 really good wavelengths. And then a 4th one, we repeat one of them, so we get stereo. So you get stereo imagery, and you get these 3 different wavelengths as you kind of just travel across the surface in a broom style. Or you can say, well, let's just have different lenses. Let's have individual cameras, and that's the design on the right here. You might want to do that if you decide somehow that a balloon can do it, but a balloon twists and turns and spins, and so in my view, you have to have frames that are taken all simultaneously, so then you can have a spectrum. Whereas on the tow body, you're more placidly going along in one direction and not really shaking as much. So we could go ahead and use this type of a broom style, taking images. Okay, next slide, please. And so here's a picture of the actual tow body, and the camera's there in the middle looking straight down. Again, it's being pulled to the right in this case at a nice steady rate, so you successively see different areas as you go across. And next slide, I think, talks about, next slide, please. And we show here the actual 4 segments again, and we go across, and here you have 50 seconds. So the point is that the speeds that we're at, we're traveling across around 60 meters per second, because it's being tied to a balloon that's up high, that's moving at 60 meters per second, and there's a 50 meter per second wind where this thing is. And so it slides across the ground, taking these successive images, and each of those segments you cover in about 50 seconds. So every 50 seconds you take a new image, and then after you're done, after around 3 minutes, you put these all together, and you get a nice image cube of those wavelengths. You can also get the stereo. So that's how that works. And the signal to noise is up there. So we get 140 signal to noise at 1.01 and about 100 at 1.0 and 70 in those images. Now each image only takes 0.16 seconds, because in 6 seconds, that's when you travel 10 meters. So we want to take an image and the time it takes to go 1 meter, one pixels diameter. The pixels are 10-meter pixels. So in 0.16 seconds, you can get these kinds of signal noise. In the end, when you finally get the data, you could go ahead and co-add 2x2, 3x3, whatever. So you just get 30 or 40 meter resolution, and the signal noise goes way up at that point. So that's another option you can use. Okay, next.
Can you wrap up quickly here?
Yeah, we're getting done here. So I'm just going to show here on that figure there, I show the error bars that we calculate based on all the data on the slide here of what we can get. So the black error bar is for 10-meter resolution, and the red error bars there in the middle are for 50 meters. We do the 5x5, and you can see those error bars. You go back. Those error bars are much smaller than a lot of the spectral structure you see up above. So we can distinguish the spectrum of surface materials this way. We might have to go to 50 meters at some point, but other times we don't. We can go with 10 meters on this. And there's other tricks we can play we'll get into later if you want. But anyway, next slide, please. Okay, and just to say, there's other types of wavelengths that we would love to look at as well, to look at water and to help with some of this interpretation, and also have a detector that actually looks at actual subcloud opacity in a general sense. So the point is, we could split this same detector up in many more segments and just take more images. I mean, just go not to be 50 seconds, but it may be every 20 seconds, you take an image, and now you can get a lot more spectra in that same one detector. Okay, next slide. And I'm going to skip over this. These are just the parameters of the mass and aspects of it. You can see that later. Next slide. And this is the summary again. So I'll just leave this up here, Jim, and take questions, but this summarizes everything that we can do. And I'll stop here.
I don't see any questions on the chat. Hopefully we'll have more by the end of the session. But I have a question, Kevin. It was mentioned earlier that the Envision and the Veritas mission will have an instrument that measures this information, but it'll be corrupted by the fact that there's a scattering in the cloud layer. Can you comment on the wavelengths that they're using for Veritas and Envision, and if there are any differences between those they're selecting than those you'd use below the clouds?
Oh, if we get back to one slide, let's back up, or 1 or 2 slides, if Tim could do that. Yeah, back up one more. Yeah, that one. So that's a slide that go back, go forward. That's too many. Got that one right there. So that's a slide that came out of Johan Helbig's paper. He's part of the which one is it? The Veritas team. And this is the kind of, and he's got about a dozen or even more, 15 or so wavelengths they're going to do. And this shows, those little bars shows what they're going to do. What we propose to do is those red ones. He's doing a lot, because from up there, if you try to do a good job, you got to handle what the cloud opacity is, and you need to decloud the atmosphere. And that means you need several more wavelengths to do that. We're below the cloud, so we don't have to do that. So there's a lot of wavelengths we don't need. However, we probably would like to do the water vapor one, for example. But this is just a small part. His spectrum goes further. I just took the central part of it. So he's doing about 15 different wavelengths, and that's good. Again, though, the best they can do is 50 to 100 kilometer resolution on the surface.
Okay, so one question here, I think this is from Colin. Are there particulate species which, if present, would render the surface imaging impractical? For example, a particle with very low albedo.
Well, we just tested out 0.9, and we could go, if we didn't test that much further, we're very encouraged to see 0.9. That's it. I think the whole thing is how much stuff you have. And, the Nolenberg-Hutton thing is very small opacity, so we kind of like that. But if it were to be above opacity of about 1 for that subcloud area, then we'd be in trouble, I think, especially if you had some albedo. But we have to go do that calculation. But the hope is that it's within, a factor of 10 of what Nolenberg-Hutton saw.
Okay, we're going to have to move on now. So Kevin, thank you. And our next presentation is by Pat McGarry, who's a robotics technologist at JPL in the Robotic Mobility Group. Patrick, received his PhD in aerospace engineering from the University of Toronto, where he was a visiting Fulbright scholar. And his research is focused on the development of systems and autonomy functions for the exploration of extreme environments throughout the solar system. So Patrick, go ahead.
Yeah, thanks. So luckily here we have a nice primer from Kevin on the science for the tow body imager. But generally speaking, we needed to go knock down some of the tall tent poles with respect to deploying a tow body, which is not a new concept per se. Some are probably familiar with the Calypso white paper. So this is a tethered tow body payload for in and subcloud sensing on Venus, and these are my co-authors. Next slide, please. So what we intended to do, we had an internal study at JPL to look at these tall tent poles, and we put these into a summary of trades. And the idea is that we want to evaluate this for subcloud imaging. So we looked at instrument suites, tethers, tow body, the management of tethers, integration, all that stuff. But what I'm going to focus on today in detail is the tether and tow body study. Next slide, please. So this is probably familiar to most people in the room. These are some of the Venus environmental parameters, but of particular concern for us are the temperature and the pressures involved at different altitudes. And so Kevin already mentioned, if we were to deploy from a balloon, so balloons are great, we can get to lower altitudes, but what we'd really like to do is get below the cloud layer. So the problem arises right away is, why don't we just place a balloon right below the cloud layer? Well, that's because the temperature is rather high at the float altitude of 47 kilometers, so it's roughly 100 C, a little bit higher actually. And the pressure goes up as well. And then in addition to that, you don't have access to reliable solar power. So just taking these constraints into consideration, what we wanted to do is understand how the tether would be laid out if we were to deploy it in an atmosphere. How long of a tether would we need? Could we do it? Could we use an optical tether and transmit the data back reliably to the balloon in case we were to lose the tow body for any reason? Next slide, please. So what we actually focused on were some environmental models and actual data from the Pioneer Venus probes. So we can kind of convolved all these into these plots here, which show with respect to altitude, how, things like wind shear vary. So we're particularly worried about wind shear because we know it's going to have an impact on the tether. In fact, when the tether is exposed to wind shears, differential wind shears, so we know this balloon is floating along at some speed, the tether is going to experience drag, which means you end up needing a much longer tether to go let's say 5 kilometers down to do this imaging. So we took these models and kind of extracted what we considered the worst case scenario for just wind shear. We did not calculate the turbulence because it's not well understood and would require pretty complex modeling. But these plots generally show the wind shears we expect, which are on the order of 10 meters per second, let's say. So next slide, please. Luckily, there's a pretty dense body of research into tow bodies in different types of mediums, especially with respect to underwater deployed sondes, that the Navy has deployed or that are for underwater research, and even some, tethered bodies from planes. So we kind of leveraged this work, next slide, please, in a very simple model. So we took this from this paper from 2003. It's a method for maneuvering marine vehicles. And we use this as a first order approximation of how long would our tether need to be and what are the tensions along the cable for deployment into a dense kind of like a dense atmosphere. And so we already know that the ocean is much more dense than the Venus atmosphere. So we use this as kind of our first order approach. But the equations are rather simple and allows us to come to some quick conclusions so we can knock down these quote unquote tall tent poles. Next slide, please. And then another thing we did is we wanted to see, okay, what if we use off-the-shelf commercial optical fiber products that are used also in the underwater industry? And so the benefit of this is that they have very, very small diameters on the order of like, the one we selected for this concept was about 500 micron in diameter. So that's very, very small. And the great thing, it has this included abrasion layer, which is meant for waterproofing, but it also turns out to be advantageous for the sulfuric environment on Venus. So it kind of has this natural protection already built in, plus it allows up to gigabit per second communication rates from the tethered tow body back to the balloon. So we know we're going to reliably pass off that data. And they have tensile properties, just a great all-in-one package, and it's off the shelf. So we took these tethers, so they're all shown here, and on the next slide, we took the model from the prior slide and tried to understand how these tethers would perform. And so one thing to note right away is the number one influencer on a tether in terms of its drag profile and its length. Its length is primarily correlated to its cross-sectional area. The tow body has pretty negligible effect. In fact, the surface area of a tether is, for let's say a basketball-sized tow body, is 200 times greater, even for a 500 micron cable over many kilometers. And so we exposed that to one of these environmental models and then tried to understand what that length and the tension would be, and if the current off-the-shelf tethers have enough factor of safety to be even considered in a first-order study. And what we found was that for many of the cables, for the lightweight cables, it turns out you actually need, on the order of 9 to 10 kilometers just to go 5 kilometers. But this is acceptable because the tensions involved along the tether are relatively reasonable and fall within the factor of safety of the cable. So these kind of just show a deployment, and note that the scales are not actually equal, they're exaggerated just to show the difference. Okay, next slide, please. Okay, so now you've seen the tether, and now we did some work on the tow body. And part of this, going into this, we know we have our imager, we know we want to include some sort of IMU to register the images. We're doing this push broom imaging study where we're kind of creating image mosaics of the surface. So we want our altitude, our stability, and our pointing to be within the regime of what the camera would allow. So we come up with some requirements, which mean which are actually pretty tight in terms of rotational stability. And we wanted to see if we could do this passively with a low power system that could hang out and do imaging for hours at a time before it has to be reeled up due to thermal reasons. Next slide, please. So, I won't go into the details of what all we did here, but just to leave you with some, basic rules of thumb for tow bodies. And this is true of aerodynamic vehicles and water too. And generally, you want to keep the center of mass under the anchor point. And if you were to see this thing in the Venus atmosphere, the tether would be roughly coming straight out of the top of the vehicle, attached to some sort of gimbal. And you want to keep your center of pressure behind that anchor point, such that you have stability for roll, pitch, and yaw. But we're looking at ways to both do this passively with design. So, the simplest shape is a sphere, and it has great rotational stability characteristics, but it's kind of it has a singularity point. So we want to play with things like booms off the end, tail feathers, and all that stuff. So the next slide, please. And then we have the question of stability. So this is kind of work to go that we're going to launch a next effort to look at is what kind of excitation, what kind of natural frequencies are introduced by the tether vibration modes due to turbulence. How can we damp those, and how can we avoid resonance? These are the problems that we would face. I'm not saying we have solutions, but we know we'd like to do it passively, but as a fallback, we could do it actively. So next slide, please. Kevin already showed this, but I wanted to talk a little bit more about what's going on here. We want to deploy from a gondola on a tether that's roughly 9 kilometers just to descend 5 kilometers so we can do subcloud imaging. The nice thing is that we have two things in our favor. We're passing through the cloud layer, so we could do in situ atmospheric sampling. And we have a tether that's made of a fiber optic. So the neat property of fiber optics is if you put gratings along the fiber at different length scales, let's say every 10 to 100 meters, you can actually measure the strain along the cable and the temperature. So you could actually use the tether as a secondary sensor. And then within the tow body itself, we have our camera, and we have some thermal control, which comes from a vacuum gap in MLI, which is totally passive. And we calculate that we can do imaging with this battery and the heating of a camera. Our primary calculations show that we can image for 10 hours before we need to reel up. And once we reel up, we need to stay at that float altitude probably for a couple days to cool it down. We might explore active ways of cooling it down, but the neat thing is that we can keep doing these deployments over and over as long as the balloon is alive and the tether remains intact. So the idea is to do this large push brim survey of the Venus surface at high resolution. And that's pretty much all I have. I'll conclude there. If there's any questions, I'll happily take them. Thanks.
Great, Patrick. Thanks so much. I don't think we have any questions at this point. But I think we'll have an opportunity later to come back to this. And in particular, I'd like to see when we get to the session at the end here, a little discussion of how this capability would compare with what Max de Jong presented earlier, where the balloon itself would descend below the clouds. So at this point, thanks, Pat. And let's go on now to the last talk of the session. And this is by Ralph Lorenz. And Ralph is going to be talking about the Da Vinci mission. So Ralph is at the Johns Hopkins Applied Physics Lab and has participated in every IPPW. Now that's impressive. He's also the author of 9 books. That's even more impressive. Most recent being Saturn's Moon Titan, Owner's Workshop Manual. And Ralph is involved in InSight, Akatsuki, the Japanese mission, Venus mission, Perseverance, and is currently the Dragonfly mission architect. So Ralph, let's hear about Da Vinci.
Okay, thank you, Jim. Good afternoon all, good evening. So the presentation, which I don't see yet, has a slight change in title from the program, a very, very happy couple of changes. The submitted abstract was the proposed Da Vinci Plus mission. And of course, Da Vinci has been selected for implementation. The plus was a proposal artifact and is no longer relevant. I'm still not seeing the slides.
Yeah, I don't see it either. Tim, can you try again? And if not, let's go to our backup presenter, Gilles.
So Da Vinci is one of 2 discovery missions selected for implementation this decade, and is led by Goddard Space Flight Center. The PI is Jim Garvin, who's worked on Venus since the early 80s. Thank you, Gilles. Yeah, I see it, though not in full screen mode. There we go.
Is it good for you?
Yeah, thank you. Let's stay on this slide. So just want to note some co-authors in the atmospheric structure investigation. Back to the first slide, please. First slide. Yeah. Just want to note the deputy PIs, Giada Arni and Stephanie Getty from Goddard, and Natasha Johnson, the project scientist. Dave Atkinson at JPL helps with the Doppler wind retrieval aspect of this investigation, and Dave Crisp, also at JPL, is a Venus veteran. A couple of colleagues in France contribute modeling expertise, and Noam Eisenberg here at APL is involved in an experiment that goes along with VASI. So next slide. Yep. And Goddard is partnered with a couple of NASA centers, as well as JPL, which provides one of the instruments. Malin Space Science Systems provides the cameras, and APL actually provides the radio system, as well as some scientific contributions. Next slide. So Da Vinci is primarily an in situ probe, a descent probe, but the carrier and relay spacecraft does carry some instrumentation that allow us to do science on the two flybys that take place prior to the probe delivery. Next slide. So the carrier instrumentation is a camera package from Malin Space Science Systems based on the OSIRIS camera suite. We'll have ultraviolet and near infrared imaging capability. We'll also be able to observe the probe deployment. We'll see the probe sailing off into the distance. There's also a technology demonstration of a compact hyperspectral imager for the ultraviolet and visible that may help diagnose the composition of the ultraviolet absorber high in the atmosphere. The descent sphere, which is in many respects patterned after the Pioneer Venus Large Probe, but with much more modern instrumentation, has a mass spectrometer to get the all-important noble gas abundances that you heard about in Paul Byrne's talk this morning. There's a tunable diode laser spectrometer to search for a number of specific chemical species with very high vertical resolution as we descend. Sulfur species, SO2, OCS, and so on. That comes from Chris Webster at JPL. The instrument that appears to be in a kit of parts at the bottom is the subject of this talk, is the pressure, temperature, accelerometer, and angular rate sensing. It isn't actually a standalone instrument box. The sensors are interrogated by an extra card that sits in the mass spectrometer instrument box. This is a much more efficient way to implement the investigation, and the sensor procurement and accommodation will all be done at Goddard. And I'm just 20 miles up the road from Goddard, so it's easy for me to work closely with the team there. There's a descent imager that looks out of the south pole of the probe, and will take outstanding close-ups as we get close to the surface. And there's a student experiment, VFOX, which Noam Eisenberg leads, that measures the sort of partial pressure or abundance of oxygen compounds. Next slide. So as with Pioneer Venus, we'll measure the entry deceleration, much in the way that Al Seif originally proposed for planetary missions. That will give us a density profile that spans from orbital altitudes, where we have a lot of in situ data both from Pioneer Venus mass spectrometer, but also Venus Express error braking. And we'll bridge the atmosphere down to the cloud tops in the conventional way. The deceleration profile is, I think, peaks at around 30 G or so. One other point about the VASI investigation, as well as scientifically, it contributes to NASA's engineering science investigation. There's some instrumentation on the heat shield, but we measure the angular rates and the deceleration during the entry phase, and in particular during the parachute deployment, and that will help feed forward to future missions to understand how over-margined or under-margined those systems might have been. Next slide. So the scientific motivation is very clear. I mean, we need the pressure and temperature context for the chemical composition measurements that are really the centerpiece of the mission. But actually, the basic thermodynamic properties of the lower atmosphere are really not well measured. We have lots of remote sensing observations above the cloud tops from various solar occultation and other techniques, spectroscopic measurements. We have profiles of pressure and temperature in some abundance down to about 40 kilometers from radio occultation. But below that altitude, the density of the atmosphere actually gets too high. The rays actually get refracted down to the surface and don't come out again. So we only have a few profiles from descent probes, and only one of those is actually really good all the way down to the surface. So the earlier Venera missions were somewhat limited in their data rate, and the Pioneer Venus external temperature sensors all failed at 12 kilometers. So we only actually have one good profile all the way down to the surface. So there's a lot of discovery potential there. Next slide. And you can see here, this is the basically the derivative of the temperature rate minus the adiabatic lapse rate. So the stability of the atmosphere from the Venera profile. And you can see, around 40 kilometers, at the bottom of the clouds, the atmosphere is very stable, very, very stratified. And then as you get lower, it becomes neutrally stable, suggesting it's convecting. And then at the bottom, there's this slightly puzzling negative stability. And if you go to the next slide, this was really underscored in some work by Sébastien Lebonnois and Jerry Schubert a few years ago, that the profile near the surface is unstable, and that just doesn't make any sense. However, it's unstable with the not unreasonable assumption of uniform chemical composition, right? That there's 3.5% of nitrogen all the way through the atmosphere. We actually know that there's a gradient higher in the atmosphere from some gamma ray measurements by Messenger. But perhaps, and there's some laboratory evidence to support this, perhaps there is actually a compositional fractionation. If you imagine carbon dioxide being delivered to the lower atmosphere from volcanoes, then that may basically displace the nitrogen upwards. And so there may be a compositional gradient. And if that's the case, then the instability goes away. And that puzzle, that's not something we see in the terrestrial atmosphere or so far any planetary atmosphere, although this sort of thing does happen in the Earth's oceans. But we can diagnose this paradox with the very abundant, high vertical resolution chemical composition measurements from Vinci and the atmospheric structure that we'll measure with VASI. The preservation of this compositional stratification, must persist in the face of mixing, and the Doppler tracking of the probe will inform the wind gradient that may drive such mixing. Go to the next slide. Yeah, we actually do two-way tracking between the probe and the relay spacecraft, which actually gives us a really good range rate precision. So these will be very good wind measurements by comparison with previous missions. The accelerometers and gyros will be working all the way down because we have such a robust radio link, which lets us do things like take pictures. We'll have very good vertical resolution on all these measurements, and so be able to characterize the turbulence at much smaller scales than has been done so far. When we get near the surface, the descent imaging will actually let us reconstruct the probe trajectory in much the same way as we did for Huygens. That gets you the three-dimensional trajectory, not just the component from the Doppler range rate. And we'll synthesize all these data together in a retrieval process. Next slide. So obviously, I think the broader community will be most excited by the descent imaging, and I think Huygens gives us a good taste of the sort of scientific impact that can have. We'll get sort of the airplane window perspective from several kilometers altitude as the atmosphere gets progressively more and more transparent in terms of its column opacity, and this will give us the ground truth. The ability to interpret radar observations from elsewhere on Venus. We'll be able to compare to the descent location in Alpha Reggio, where we have both radar data from Magellan and from the upcoming missions, and the local optical view. Next slide, I think, is the last. Yeah, so you know, Venus is the exoplanet next door. Venus is the Earth's twin that you know, took a wrong turn, and the suite of measurements that Da Vinci will make will be revolutionary in our understanding of Venus. And I'm very happy to play a small part in all that with the Vasi investigation. Thank you.
Thank you, Ralph. I don't see any specific questions for Ralph at this point, but I have one. We heard from Patrick earlier about the stability of the platform and how that would influence imaging from this tow body. Ralph, can you give us any indication of how well the probe will be stabilized as it descends, and what sort of maximum spatial resolution can we expect from the probe?
Well, the spatial resolution gets close to infinite, you know, as you get within a few meters of the surface. I forget how many seconds before impact the last image will come off, but I think in principle, geometrically, the pixel scale will be, you know, 10 centimeters or something like that. Whether, you know, that image gets off the probe in its entirety before impact remains to be seen. So as with Huygens, post-impact survival is not guaranteed, but it may happen, right? One of the 4 Pioneer Venus probes continued to operate after impact, and we might get lucky. You can maybe just see in the picture there are little spin vanes around the perimeter of the probe. Those help improve the stability during descent, but that is something we'll be looking at in the risk reduction phase that we undergo before we go into phase B. There is a neat trick that we can do with the camera system when an image is blurred by motion, and you know, maybe a handful, 2 or 3 out of the 100 or so Huygens descent images were actually motion blurred. But when you get a motion blur, there is effectively a low-pass filtering of the image, albeit by a, you know, non-square filter kernel, and that results in loss of information. And the images are in effect JPEG compressed, which is a, you know, Huffman-coded discrete cosine transform. And so the file size of an image that has been smeared by motion blur is actually smaller than the equivalent unsmeared scene. And so we can actually prioritize that the probe sends the images with the highest entropy, the highest information content, i.e. it prioritizes the least blurred images. So, you know, we should be pretty robust to probe motion, but obviously it's something we'll pay attention to.
Very good. Well, I see Jim Garvin indicated there would be 14 to 20 centimeter pixel unblurred images in 2 bands, narrow and broad, with best resolution from 2 kilometers to the surface. And we'll be acquiring images at 200 meters scale under the hazes and down to tens of centimeters near the surface. Very exciting. So I think this brings the presentations to a close. I want to thank Ralph. Very interesting and to hear, at least for me, for the first time in any detail about Da Vinci. Very exciting mission. We are going to have a little time here for questions. We did get delayed a little bit. We had some technical problems. Thank goodness we did not rely on a single string approach for presentation. Tim Bryce got kicked off entirely, so he's gone. And thanks for Gilles for stepping in. So let's see. Colin, do you want to come in at this point and see if you have any questions as we go to the session? And then we'll spend some time discussing the presentations in this session, and then we'll go to all of the poster talks in about 5 minutes. Does that make sense? Oh, okay. So I had a question here for both Max and Patrick. You presented 2 different approaches to getting below the cloud layer for imaging. Would you like to comment on the relative merits of these approaches? Maybe we could start with Max. Max, are you still here? Well, maybe Max is not still here. So Patrick, I'll let you do it.
Yeah, I'd say the tethered approach, I think it offers a lower cost, lower complexity, safe means to access subcloud layers. I think it would be wonderful to take a balloon as well. I just think it has, it's probably from a mission standpoint, it makes more sense not to dangle things from spacecraft that are on tethers of multi-kilometers. But I think if you work into the details, the fact that the tow body is essentially not as reliant, there's not as strong of a coupling to the pressure. The balloon has to have pretty good control. You'd have to, anytime you don't want to stress your primary flotation method, but I would defer to thinking that the balloon, if in a perfect world, balloons would be great. If you could just descend below the cloud layer, that'd be fantastic. But I think the temperatures make it rather risky. And the tow body is essentially an add-on payload that you could do on current Venus balloon missions. So you wouldn't have to have any built-in balloon. You could just take things that have flown before and attach this low mass payload. So I maybe didn't mention, but the tow body itself with the camera is about 5 kilos. And the entire system with the tether management and the tether, that would all be under 30 kilos. So the whole thing is just 30 added kilos to an already conceived Venus mission. So that would be my take on it.
Okay, thanks for that. So we now have a couple of questions that would specifically go to Ralph. And maybe Jim Garvin, who's online here. Are there rideshare opportunities on Da Vinci's launch vehicle or interplanetary bus? This is from Nicholas Dietrich. Maybe Jim would like to take that one as the PI.
Well, Jim, I think my dog is reacting. Can you guys hear me?
Yes.
NASA headquarters is the owner of the asset beyond the primary mission, everyone. So the system architecture we have has various capacities that could be extended or utilized, and that's up to Thomas Verbuchen and his team to use them. Our spacecraft is designed to do flybys and drop a probe and relay, and could eventually get into Venus orbit as per NASA headquarters. So those capabilities and assets will be, under assessment by our stakeholders at NASA headquarters. So we really, can't talk about what they may have in mind. I think the same is true for Veritas and other missions. So that's all I can say. I don't know if Ralph, if you or anyone else would like to comment.
No, that's the exactly the same paradigm as Dragonfly, and NASA headquarters determines whether there are any opportunities or not.
Okay, good. So we have a question from Bernie Beanstalk. Any details on telecom between the probe and carrier vehicle? I'm sure Bernie would like to know how many images you're going to be able to get back in particular.
Yeah, that particular question, Jim already answered in the chat. Hi, Bernie. Yeah, I guess for now, I'll just say the link is S-band, and it uses adaptive data rate, right? The system monitors the two-way link margin and steps the data rate up as the carrier relay spacecraft gets closer to Venus. So we really maximize the data return that we can have.
Okay, good. I have a question for Kevin Baines, and it really relates to what Paul Byrne presented in his presentation. He indicated that there had been evidence of not just past volcanism that had left unweathered deposits, but current volcanism, hot areas. What would your technique do if it were to encounter areas that were hotter than the surrounds, not just different emissivity. Will it provide any important information?
Yeah, well, this technique is very sensitive to the surface temperature. And in fact, we have to know the elevation, to really get the spectrum really well. Although, the surface glow does not vary that much. What it varies with wavelength, that's what we're going to use. But if we had no idea at all what the surface elevation was, we'd be really confused. So you have to know the elevation to some extent, and so therefore we can measure, and the elevation changes by 8 degrees. Temperature changes 8 degrees per kilometer of elevation, and we can easily see, down half a degree, even less, probably 0.1 degrees. So we can sense temperatures very accurately. And so hopefully the radar maps that we get, we've already got Magellan radar maps, and hopefully the new ones that'll come out of these other missions, we can use those too to kind of really tell what the elevation really is. So the point is, if we see, an area that we think is, one type of geological plane or something, all of a sudden we see a bright spot in it that doesn't correspond with the altitude, just in one wavelength, that's just using one wavelength, not using three, you could easily tell that the temperature has changed a lot. So temperature is a simple thing for us to measure, really, and we can do it again at 10-meter scales if we had to. So anyway, so it should be very simple if it's an active volcano at all. And even if it's not an active volcano, I think there's probably warm spots that maybe little fumaroles and things that are happening, and we probably could sense a fumarole if from this thing. So it might be interesting to see what we get. So that answers that pretty much.
Okay, good. So, Colin, do you want to come back on and make some closing remarks here, perhaps?
Well, I just wanted to shout out to our poster presenters. Actually, Bernie Beanstalk's question about data relay rates makes me think of a very similar question on a much smaller distance scale, which is in the architecture proposed by Gilles Bellet and also Ian Moore, who were talking about deploying little tiny probes with 10-gram payloads from a balloon and then tracking them. Now the payload, I do encourage you to have a look at the posters, which are on the website. But one question is how long do these last, and the data rates you can get with that? Can you say something about that, Gilles?
Yes, so it's a problem that we actually are pursuing for a few years now for different applications, and actually we are able to have them powered for several hours. So of course on Venus they're gonna have a really short lifetime, maybe like half an hour, and we're actually able to get something about between 18 and 24 bytes per second. So that's not that much, but that's actually really interesting if you want to do some distributed measurements and for some specific mission design, such as, for example, detecting eruption columns on Venus. That's actually more than what we need, to validate or not, for example, the detection of that CBAF will do with his ultrasound instrument.
And in terms of, by the way, if anyone else has questions for Gilles or his collaborators, put them in the chat, please. But just one further question, Gilles, is your position knowledge for where your microprobes are, does that come solely from the IMU, or are you also tracking them with the radio system?
Actually, we have a new technique, so it's not fully published yet, but it's pretty interesting. We are using the signal strength, and actually we are able to have, for example, if you release several of the probes, you're actually able to have a really precise determination of the trajectory of every node with an anchor, which is actually the balloon. So you can really reconstruct, the measurements at the exact location where you made them during the whole trajectory.
Excellent. So there's another question for you in the chat. This is from Manuel Dominguez. What time response are you expecting for your SO2 gas sensors? I guess we should ask what type of SO2 gas sensors you're using, and how sure are you that they're sensitive to SO2 and not cross-sensitive to other species?
So those are commercial instrumentation. So we'll need, of course, to make them, make sure that they're going to be able to survive Venus. But they're actually really sensitive. And what is really interesting is actually for the eruption column, in our specific case, the concentration will be much higher than any other kind of signal that will be mismatched for something else. So actually, we have a really fast response time. We do almost instantaneous measurements, and because we have such a low velocity for these platforms, we're gonna have like some true measurements. It will not be, bothered by the backshell disturbances or anything like that.
Great. Thank you for that. There's a question for Ian Moore. Are the femtoprobes planned to drop all at once from 55 kilometers or staggered throughout the entry trajectory?
So Jan had to leave, so I will answer for him. So actually, we're gonna release them by packets of 8. So we are releasing them by 8 to have this, this network disposition to be able to establish the exact position of each of the nodes. And by releasing them by packet of 8, we're able to deploy 64 in total to actually cover different latitudes along the entry path. So we're able to really make some really interesting measurements, not just on one, vertical trajectory, but actually in 64 of them.
Excellent. This sounds reminiscent of a technology reference study conducted by ESA some 15 years ago called the Venus Entry Probe mission. So any fans of this work, I recommend you look that up as well. Shall we switch to another poster presenter? There's a question that's just come in for Javid Bayandor's presentation, so we might as well take that. So this is for Tandem, which is a tensegrity structure to support both the entry shell and a rover on the surface. So have a look at that poster, and the question is, what is the expected payload size for this system Tandem, and how scalable is the concept?
Hi everyone, thank you for the question. At the moment we're focusing on 50 kilograms corresponding to vitals, basically mission objectives and instrumentation. Is this, did you hear me?
Yes, great. Yes, sorry, I was muted. Can you just outline in 30 seconds, are you using the tensegrity structure both for supporting the air shell in the top phase of flight and for deceleration at the bottom and for crush resistance when you land, as well as mobility?
Yes, I think advantage of using the tensegrity structure is that it can create a unique EDL and then -L system. Not only we can enter, descent, and land, but also after we land on the ground and we find a firm footing, we can locomote as well. So this is the only system right now that includes just a shock plate together with a drag plate to be able to also, while it's coming down through descent, it can navigate the atmosphere and can collect data before its final impact onto the ground. And the tensegrity structure is designed so that it can protect the payload module that sits right in the middle of the system. There is a nice video in my poster. It only takes 2 minutes. If colleagues would like to have a look at that, that probably shows them a little bit of better impression of what the system is.
Excellent. Have you already looked at high temperature systems like motors and so on to be able to work out sort of realistic mass budgets for whole missions involving this, or have you just looked at the tensegrity structure?
No, that's one of the things that we are currently looking into. We have the privilege of working with NASA Langley and NASA Ames, and we are sort of dissecting that project as we go forward, and we have a team that looks into the high temperature electronics and high temperature structures as well.
I have a question for Mark Murbach, if Mark is there. And it concerns this concept you have for a very small probe that could be compatible with what Rocket Labs has been talking about. Can you amplify how far you can scale down that probe and whether you really can relay data or communicate data directly to Earth.
Good morning, everybody. Thank you for the question, Jim. I appreciate it, and it's nice to see everybody. In fact, the subtitle of that paper, or the poster, would have been, "What can you do with 15 kilograms and 1 electron?" So that's exactly what you were asking. And the mission analysis that we've seen, basically the size of the probe that you could do with this new space approach would be in the order of 15 to 20 kilograms. The exercise that we undertook was actually doing, it's a 3U nanosatellite with a sufficient heat shield or TPS entry system. So how do you go about doing that? So we first have to work through the swap and COM, size, weight, power, and COM. Can you close it? So because if you can't do that, then nothing else matters. So the proximity of the Earth following the architecture of the Pioneer Venus seemed to work. We want to have the entry probe, supposed entry probe, in close proximity, but also using the upper stage, the photons, at least a temporary relay. So trying to close it both with SRX and a UHF with this little bit more forgiving antenna pattern to the relay. That seems to be on the verge of being feasible. And then the other note is, in order to make this happen, we were focused really on making atmospheric measurements with our colleagues at MIT. So really interested in the 70 to 40 kilometer band. Did I do that right? Yeah. And not have a pressure shell. The pressure shell weighs a lot. So just as a real quick note, the Pioneer small probe was 90 kilograms and a ballistic coefficient of 200 kilogram per meter squared. We're looking at something that is 1/6 of that. And then with the necessity of increasing, basically making a shallower entry, so having a shallower entry angle for greater dwell time, and also decreasing the ballistic coefficient as much as possible. So we found that with the legacy approach, we could get to around 35 kilograms per meter squared. Depending on the risk posture, we can take another step and actually reduce that even further, but the latter would require a flight test in order to understand that a little bit better. So all told, I would, in terms of framing this properly, the DS2 was ambitious and I think an important endeavor. I think that was a more difficult endeavor than packaging several small instruments with this probe in 15 kilograms. I think all of the technologies that have advanced that is just on the verge of practicality.
Okay, do we have any more questions on posters?
And here I am.
We are half an hour past our scheduled time. Maybe now's a good time to draw matters to a close.
I think
more questions.
I think that's a very good suggestion. So I'd like to thank everybody for participating. I think this has been a very stimulating session. I think we managed to cope with our technical problems quite well. Apologize for running late. I think we were just overly ambitious in the schedule, and I think we didn't want to originally schedule for quite as much time, but consequence, we didn't really do justice to the posted papers. So I hope we have now, and I'd like to thank you all. So Colin, do you want to draw things to a close?
I just see Pat has a raised hand. Pat Beecham, did you want to say something?
Yeah, hi, thanks, Colin. What I was just going to do is advertise the next session on August 10th, which is on future missions. And if people want to go take a look at the agenda, it's on the IPPW website. And the posters will be shown in a couple of days on that site. So they might want to people might want to go take a look at the posters on that site, maybe at the end of this week. Thanks a lot.
Excellent. Thank you, Pat. I think just one other thing to advertise is that if you're new to all things Venus, or if you're an old hand at all things Venus, the place to be is the VEXAG annual meeting, the Venus Exploration Analysis Group, which will be in November at APL in a new, bigger venue than ever before. So there's plenty of room for you to show up, and it's not just talking about existing Venus missions, it's also new priorities, new possibilities for future Venus missions. So all these kinds of presentations would be welcome there as well. So with that, I'll echo Jim's thanks to everyone for participating, and see you at the next IPPW session. Thank you to all the presenters.